The moment you leave the solar system, every single system keeping you alive becomes a countdown timer, and the nearest hospital is 4 light years away, traveling at the speed of light. You crossed the impossible distance. You did what every astronomer who ever lived only dreamed of, but you realize reaching interstellar space was the easy part. If this kind of content speaks to something inside you, please subscribe to the channel. Now let's get started. Humanity has dreamed of traveling to other star systems for as long as we have understood what stars actually are. And that understanding, believe it or not, is relatively recent. It was only in the 19th century that scientists began to accurately measure just how far away those tiny lights in the sky truly are. The nearest star system to our own is Alpha Centauri, a triple star system sitting at approximately 4.2 light-years from Earth. That number sounds compact. It is not. 1 light-year is the distance light travels in a full year, moving at roughly 1 billion kilometers per hour. Multiply that by 365 days, 24 hours a day, and you get approximately 9.5 trillion kilometers. Now multiply that by 4.2. The result is a number so staggering that the human brain genuinely struggles to hold it. If you want to really feel what that distance means in practical terms, in terms of time, fuel, and the crushing patience it would demand, I actually covered this in detail in another video on the card above. I highly recommend watching that one alongside this. It gives you the raw numbers and what they mean for any mission we might realistically attempt. The link is in the description and pinned on the comments. But here is the thing. Even once you have wrapped your head around the sheer distance, even after you have accepted that any interstellar journey would take generations or would require technologies we have not yet invented, there is still a much more immediate and unsettling problem waiting on the other side of that mental leap. What is actually out there? What fills the space between stars? And what does it do to a spacecraft or a human body traveling through it? The first thing most people assume about interstellar space is that it is a perfect vacuum, a total void, nothing there at all. And compared to the air surrounding you right now, that assumption is mostly correct. But mostly correct hides a great deal of danger. The region between stars is called the interstellar medium, and it is not empty. It is filled with an extraordinarily thin mixture of gas and dust, primarily hydrogen, about 90% of it, along with helium, and trace amounts of heavier elements forged in the hearts of long-dead stars. On average, there is roughly 1 atom per cubic centimeter of interstellar space. Compare that to the air in your room, which contains approximately 10 to the power of 19 molecules per cubic centimeter. That is 10 followed by 19 zeros. And yes, interstellar space is effectively empty by any standard we experience in daily life. But here is where it gets interesting and dangerous. A spacecraft traveling at even a small fraction of the speed of light, say 1%, which works out to roughly 3 million kilometers per second, would collide with those sparse atoms and dust particles at an energy level that transforms them into something terrifying. At those velocities, even a single hydrogen atom hitting the hull of your ship carries the punch of a small particle accelerator blast. And over the course of years or decades of travel, those collisions accumulate. They erode surfaces. They generate secondary radiation. They heat materials in ways that are extraordinarily difficult to predict or control. The famous Breakthrough Starshot initiative, announced in 2016 by a coalition of scientists that included the late Stephen Hawking, proposed sending tiny laser-propelled spacecraft toward Alpha Centauri at about 20% the speed of light. One of the biggest engineering concerns raised almost immediately was not the propulsion system. It was erosion. At 20% the speed of light, the interstellar medium effectively becomes a sandblaster operating at subatomic scales. even the most resilient shield material we can currently engineer would be worn down over the course of a 20-year journey. Researchers like Dr. Renée Heller at the Max Planck Institute for Solar System Research modeled this problem extensively and found that the leading edges of any such craft would need to be incredibly thin and shaped in very specific ways just to survive the journey at all. And even then, the damage would be significant. Now scale that up. Not a centimeter-wide chip traveling light, but a crude spacecraft massive enough to keep human beings alive for years or decades. The surface area exposed to the interstellar medium grows enormously, the structural complexity multiplies, and suddenly, the erosion problem goes from a fascinating engineering puzzle to a genuine existential threat for anyone on board. This is just the first layer of the challenge, and we are barely getting started. There is something else out in that darkness that is perhaps even more insidious than physical erosion, something you cannot see, cannot feel in the moment, and yet accumulates inside your body with quiet and devastating efficiency. We are talking about cosmic radiation, and specifically the variety that originates not from our sun, but from the most violent events in the known universe. Galactic cosmic rays are high-energy particles, mostly protons and atomic nuclei, that have been accelerated to extraordinary velocities by supernovae explosions, neutron star collisions, and the environment surrounding black holes. They travel through the galaxy in every direction, and here on Earth, we are almost entirely shielded from them. Our planet's magnetic field deflects a massive portion of them. Our thick atmosphere absorbs much of what gets through. We live, essentially, under a double layer of protection that we never have to think about. The moment you leave that protection behind, the equation changes completely. Astronauts aboard the International Space Station, which sits only about 400 kilometers above Earth's surface, still well within the influence of our planet's magnetic field, already receive radiation doses significantly higher than people on the ground. Studies from NASA and the European Space Agency have shown that long-duration stays on the station measurably increase an astronaut's lifetime risk of certain cancers. And the station is still close to home, still partially shielded. Now imagine leaving that bubble entirely. Voyager 1, launched in 1977 and now the most distant human-made object ever sent into space, crossed what scientists call the heliopause in 2012. The heliopause is the boundary where the sun's influence, its magnetic field and solar wind, gives way to true interstellar space. Data sent back by Voyager 1 after crossing that boundary confirmed what physicists had long suspected. Cosmic ray intensity increases sharply once you leave the heliosphere. The sun, it turns out, has been acting as a partial shield for the entire solar system all along. Step outside it, and the radiation environment becomes considerably more aggressive. For a crewed mission, this is not a theoretical concern. It is a hard biological limit. The human body can only absorb so much ionizing radiation before the damage becomes irreversible. DNA strands break, cells mutate. The central nervous system, particularly sensitive to certain types of heavy ion radiation, can suffer damage that no amount of medical treatment can fully reverse. Researchers studying the Mars mission problem, which would expose astronauts to deep space radiation for roughly 6 to 9 months each way, have already identified this as one of the primary barriers to long-duration human spaceflight. And Mars is still inside our solar system, still receiving some degree of protection from the sun's magnetic influence. An interstellar voyage would mean years, decades, possibly centuries of uninterrupted exposure to the full intensity of the galactic cosmic ray environment. Every year spent in that radiation field chips away at the biological machinery that keeps a human being alive and thinking and functioning. And the cruel irony is that the faster you travel, the sooner you arrive, the worse the radiation problem becomes in a different way, because higher velocities mean the particles you encounter carry even greater relative energy. There is no clean solution to this on the table right now. Passive shielding, surrounding the crew compartment with thick layers of material, helps, but only up to a point. Water, polyethylene, and certain hydrogen-rich materials are among the best absorbers of cosmic radiation we know of. But to shield against the heaviest and most energetic cosmic ray particles, you would need so much mass around the crew that the spacecraft itself becomes impractically heavy. Active magnetic shielding, essentially creating an artificial magnetosphere around the ship, has been studied, but the energy requirements and engineering complexity are immense. As of today, it remains firmly in the conceptual stage. This is not a reason to abandon the dream. It is a reason to understand it honestly. And understanding it honestly is how we eventually solve it. The universe has a temperature. And that temperature, in the depths of interstellar space, is almost nothing. We are talking about approximately 2.7 degrees above absolute zero, the theoretical point at which all molecular motion stops entirely. That number comes from something called the cosmic microwave background radiation, the faint thermal echo of the Big Bang itself, still filling every corner of the observable universe nearly 13.8 billion years after that first explosive moment of creation. It is one of the most beautiful and humbling discoveries in the history of science. It is also, from an engineering standpoint, a profound problem. Managing temperature in space is not the same as managing temperature on Earth. Here we are surrounded by air. Air conducts heat away from hot objects and transfers warmth to cold ones. It is an invisible but constant mediator between us and the temperature extremes of our environment. In space, that mediator does not exist. Heat can only move through radiation, the emission of infrared energy, and that changes everything about how a spacecraft heats up, cools down, and maintains the narrow thermal range that human biology and sensitive electronics require to function. On one side of a spacecraft pointed toward a star, temperatures can climb to hundreds of degrees. On the shadowed side, facing the void, surfaces radiate heat away into that 2.7 Kelvin background and can plunge to temperatures that make Antarctica feel tropical. Managing this gradient, keeping the inside of a crewed vessel at a stable, livable temperature, while the outside experiences swings that would destroy most materials, requires constant active work. Heating systems, cooling loops, radiators, thermal insulation layered with extraordinary precision. Now consider what happens when, after decades of travel through interstellar space, a component in one of those systems fails. There is no ground crew to call, no replacement part waiting in a supply depot, no possibility of a rescue mission. Whatever breaks, you fix with what you have. Whatever you cannot fix, you learn to live without, or you do not survive to reach your destination. The engineering redundancy required for a crewed interstellar mission is not simply a matter of building two of everything. It is a matter of building systems that can repair themselves, adapt to failure modes that designers could not anticipate, and keep functioning across timescales that no machine in human history has ever been tested against. We have some precedent for long-duration spacecraft survival. The Voyager probes, again, are the gold standard here. Launched in 1977, both spacecraft are still operational as of the early 2020s, an extraordinary achievement that their engineers are justifiably proud of. But the Voyagers are not crewed. They carry no life support systems. They require no food, no water, no breathable atmosphere. They are extraordinarily simple compared to what a crewed interstellar vessel would need to be. And even they have experienced system degradations, communication difficulties, and software anomalies that required creative problem-solving from teams of engineers across decades. Now imagine that same challenge multiplied by orders of magnitude. A vessel carrying human beings needs breathable air, which means a closed-loop life support system recycling oxygen from carbon dioxide, processing waste, maintaining atmospheric pressure and composition with essentially zero margin for extended failure. It needs water, recycled, filtered, re-purified in a continuous loop, because there is no resupply. It needs food, either stored in quantities that represent an enormous mass and volume problem, or grown aboard the vessel in agricultural systems that have never been tested at interstellar scale. It needs warmth, light, gravity simulation, medical facilities, and the psychological infrastructure to keep human minds functioning coherently across years or generations of isolation. Each one of those requirements represents its own deep engineering problem. Together, they form a web of interdependencies so complex that a failure in one system can cascade rapidly into failures in others. And in interstellar space, there is no margin. Every gram of resource, every watt of power, every hour of crew time spent on maintenance is a gram, a watt, and an hour that cannot be spent on something else. The International Space Station offers a glimpse of this challenge at small scale and short duration. It is arguably the most complex machine ever built by our species, maintained by a rotating crew of highly trained specialists, resupplied regularly by cargo missions from Earth, and capable of being evacuated in an emergency. Despite all of that support, it requires constant maintenance, experiences regular equipment failures, and has demanded extraordinary improvisation from crews over its operational lifetime. A crewed interstellar spacecraft would be the station stripped of every external safety net, scaled up dramatically, and sent on a journey from which no emergency return is possible. This brings us to something that does not get discussed nearly enough in popular science conversations about interstellar travel, the problem of time itself. Not time dilation, though that is real, and we will get to it, but the simpler, more immediate problem of what decades or centuries of elapsed time does to every physical system aboard a spacecraft. Metal fatigues, seals degrade, lubricants dry out, insulation cracks, electronic components drift out of calibration. Software accumulated over decades develops subtle errors that compound in unpredictable ways. Biological systems, the bacteria, fungi and microorganisms that inevitably share any enclosed human environment, evolve in the closed ecosystem of a spacecraft, potentially developing resistances, new behaviors, or entirely novel characteristics that nobody designed for. The human immune system, deprived of the constant microbial challenge it faces on Earth, may weaken in ways that make crew members vulnerable to pathogens that would be trivial threats at home. These are not hypothetical worries invented by pessimists. They are documented phenomena observed aboard the International Space Station and studied extensively by researchers at NASA, the European Space Agency, and space medicine institutions around the world. We know that microbial communities change in the closed environment of a space station. We know that the immune system responds differently in microgravity. We know that materials degrade in the radiation and thermal cycling of space faster than they do on the ground. We know all of this from a station that sits 400 kilometers above our heads and receives regular supply missions. Extrapolate those findings to a vessel that will not return for generations, and the picture becomes sobering. There is another dimension to the time problem that cuts even deeper, and it lives not in the machinery of the spacecraft, but in the minds of the people aboard it. Human beings are social creatures shaped by millions of years of evolution on the surface of a living planet. We are wired for open skies, changing seasons, the presence of other people, the ability to walk somewhere new. We need novelty, we need nature, we need the feeling that the world around us is larger than ourselves. A spacecraft, no matter how thoughtfully designed, is a closed box. a beautiful, extraordinary closed box, but a box nonetheless. The psychological toll of long-duration isolation and confinement is one of the most serious and least glamorous challenges in human spaceflight. Studies conducted in analog environments, submarine crews, Antarctic winter over stations, the Mars 500 simulation conducted in Moscow between 2010 and 2011, in which 6 volunteers spent 520 days in a sealed facility simulating a Mars mission, have all documented the same broad patterns. Interpersonal conflict escalates, motivation declines, sleep quality deteriorates, cognitive performance dips in subtle but measurable ways, depression and anxiety become more prevalent, and those studies involved crews who knew they could leave if things became truly unbearable, crews who were in communication with the outside world, crews who knew that their isolation had a fixed end date measured in months, not years. An interstellar crew would face all of that, magnified enormously, with no escape valve and no guarantee of what waits at the destination. The psychological architecture required to sustain healthy human minds across a multi-decade or multi-generational voyage is something we do not yet know how to build, because we have never had to. It is a challenge that sits at the intersection of engineering, medicine, sociology, and philosophy, and it may ultimately prove harder to solve than any of the physical problems we have discussed. Let us talk about gravity, or more precisely, the absence of it. When you picture a spacecraft drifting through interstellar space, you probably imagine the crew floating weightlessly through the corridors, moving with that effortless, almost dreamlike grace you have seen in footage from the International Space Station, and there is something undeniably beautiful about that image. Zero gravity looks like freedom. It looks like a superpower. But the human body, after prolonged exposure, tells a very different story, one written not in poetry but in bone density scans, muscle atrophy measurements, and fluid shift data collected painstakingly by researchers who have spent decades trying to understand what happens to us when we leave the gravitational embrace of our home planet. The effects of microgravity on the human body are extensive, well documented, and in several cases deeply concerning for long-duration spaceflight. Within days of entering a weightless environment, the body begins to redistribute its fluids. On Earth, gravity pulls blood and other fluids toward the lower body. In space, that gradient disappears and fluids shift toward the upper body and head. Astronauts frequently describe a persistent feeling of nasal congestion and facial fullness, not unlike having a mild head cold that never goes away. This fluid shift also increases pressure on the eyes, and over time it can cause structural changes to the eyeball and the optic nerve that result in measurable vision impairment. This condition, called spaceflight-associated neuroocular syndrome, or SANS, was not fully recognized until relatively recently. Data collected from astronauts returning from long-duration missions aboard space station revealed that a significant proportion of them experienced meaningful changes in visual acuity during their time in orbit. Some of those changes persisted after return to Earth. Researchers at NASA and universities across the United States have been studying this intensively because it represents a genuine threat to mission safety. A crew member whose vision degrades significantly during an interstellar voyage cannot simply put on a pair of glasses and carry on. The underlying cause, intracranial pressure elevated by fluid redistribution, requires interventions that go far beyond corrective lenses, and that is only one system affected by microgravity. The musculoskeletal system takes some of the heaviest hits. On Earth, your bones and muscles are in a constant low-grade battle against gravity. Every step you take, every time you stand up from a chair, every time you carry something across a room, you are loading your skeleton and working your muscles against gravitational resistance. Remove that resistance entirely, and the body responds with brutal efficiency. It stops maintaining mass it no longer needs. Bones begin to lose density at a rate that in long-duration spaceflight can reach about 1 to 1.5% per month in the most affected regions. The lower spine, the hips, the upper femur, muscles shrink. The postural muscles of the back and core, which work constantly on Earth just to keep you upright, atrophy with particular speed. Astronauts aboard the International Space Station follow rigorous daily exercise regimens specifically designed to slow this process. 2 hours or more per day on resistance machines and aerobic equipment engineered for use in weightlessness. And those regimens work to a degree. They significantly reduce but do not eliminate bone and muscle loss. They also consume an enormous amount of crew time and energy that could otherwise be spent on mission tasks. And the equipment required to sustain that exercise, heavy, mechanically complex, requiring regular maintenance, adds mass and complexity to an already extraordinarily demanding spacecraft design. For a journey of years or decades, the math becomes uncomfortable. Even with the best mitigation strategies currently available, bone loss over a multi-decade voyage in true zero gravity would likely leave crew members structurally compromised in ways that could not be fully reversed. And there is a harder question hiding behind that one. What does it mean for a crew member who was born aboard an interstellar vessel who has never experienced planetary gravity in their life to eventually arrive at a destination world with a gravitational field? Their skeleton, their muscles, their cardiovascular system, all calibrated by a lifetime in weightlessness, would face a crushing adjustment to a world that evolution designed our bodies for, but their bodies have never known. The solution that comes up most frequently in serious aerospace engineering discussions is artificial gravity through rotation. If you spin a cylindrical or ring-shaped section of a spacecraft at the right speed and radius, the centrifugal effect experienced by anyone inside mimics the pull of gravity. The physics are well understood. Arthur C. Clarke wrote about it. Stanley Kubrick depicted it memorably in 2001, A Space Odyssey. It appears regularly in serious conceptual spacecraft designs produced by researchers at institutions like NASA's Advanced Concepts Division and the European Space Agency's long-duration mission planning groups. But implementing it in practice introduces its own formidable set of problems. The Coriolis effect, the tendency of moving objects to curve in a rotating reference frame, creates disorientation and nausea in human beings when the rotation rate is too high or the radius too small. To produce Earth-like gravity at a rotation rate slow enough to avoid serious Coriolis effects, you need a spinning structure with a radius of at least several hundred meters. That is an enormous engineering undertaking for a structure that also needs to be launched from Earth, survive the journey, and function reliably for decades without significant maintenance support. And even if you solve the engineering challenge of building such a structure, you introduce new complexities. Rotating sections must interface with non-rotating sections, the parts of the ship that need to remain stable for navigation, communication, and observation, bearings, seals, and rotational joints that must function without failure for decades in a radiation-saturated, thermally extreme environment represent some of the most demanding materials engineering challenges imaginable. The failure of a rotational joint on an artificial gravity ring during an interstellar voyage is not a manageable inconvenience, it is potentially catastrophic. All of this circles back to a fundamental truth about interstellar travel that is easy to overlook when the conversation focuses on propulsion and distance. The human body is not built for it. We are creatures of a particular planet, shaped by a particular gravitational field, a particular atmospheric composition, a particular radiation environment, a particular cycle of light and dark. Every day we spend away from those conditions is a day our biology registers as an emergency and responds accordingly. Medicine and engineering can push back against that response remarkably effectively, as the careers of astronauts like Scott Kelly and Christina Koch demonstrate, but they cannot eliminate it. Not yet. Not with anything we currently have. Scott Kelly spent 340 days aboard the International Space Station in a landmark study designed to measure the biological effects of long-duration spaceflight by comparing him to his identical twin brother Mark, who remained on Earth. The results, published across a range of scientific journals and summarized in a comprehensive 2019 paper in the journal Science, were striking. Scott showed changes in gene expression, telomere dynamics, gut microbiome composition, cognitive performance, and inflammatory markers that his brother did not. Most of these changes reversed after Scott returned to Earth, but some did not, and the ones that persisted served as a reminder that the cosmos extracts a biological price for extended residence. 340 days is extraordinary by current standards. An interstellar journey, even under optimistic projections, would measure its duration not in days but in decades. The biological price of that journey, paid continuously, compounding with each passing year, is something we are only beginning to understand how to calculate. There is one more dimension of the gravity problem that deserves attention, and it connects to the largest scales of physics. What happens to time itself when you travel at a significant fraction of the speed of light? Einstein's special theory of relativity, confirmed experimentally more times than we can count, built into the GPS system that helps you navigate every single day, tells us something profoundly strange about time at high velocities. The faster you move, the slower time passes for you relative to someone who is stationary. This effect, called time dilation, is negligible at the speeds we experience in everyday life. But at 1020, 50% of the speed of light, it becomes significant. At 90% of the speed of light, it becomes dramatic. At 99%, it becomes world-altering. A crew traveling to a star 4 light-years away at 99%, the speed of light would experience only a fraction of the time that passes on Earth during their journey. They might arrive having aged only months while Earth has aged years. They might leave behind everyone they have ever known, every institution, every cultural reference point, and return, if they return, to a world that has moved on without them in ways they cannot predict or prepare for. And if the journey takes them far enough, at speeds close enough to light, the time dilation effect means they could theoretically travel extraordinary distances within a single human lifetime, while billions of years pass outside. It is one of the most staggering implications of relativity, and it raises questions that go far beyond engineering, questions about identity, about belonging, about what it means to be human in a universe where time itself is not a constant shared experience, but a variable shaped by motion and gravity. Who are you when everyone you loved is gone? What is home when home no longer exists in the form you remember? These are not questions with engineering solutions. They are questions that reach into the deepest parts of what it means to be a conscious being embedded in time, and interstellar travel forces them into the open with a clarity that is at once thrilling and heartbreaking. There is a moment somewhere beyond the orbit of Neptune where something changes, not physically, not in any way you could feel or see from inside your spacecraft. But in terms of your relationship with the rest of humanity, a threshold gets crossed that is difficult to fully appreciate until it happens. The signal you send back to Earth, traveling at the speed of light, the absolute speed limit of the universe, takes so long to arrive that conversation becomes impossible, not difficult, not inconvenient, impossible in any meaningful sense of the word. Right now, signals from Voyager 1 take more than 22 hours to reach Earth one way. That means any question sent to mission controllers takes more than 44 hours to receive a response. And that is for a probe that has only traveled about 23 billion kilometers from home. Alpha Centauri is approximately 268,000 times farther away than that. A signal sent from a spacecraft halfway to Alpha Centauri would take over 2 years to reach Earth, and another 2 years for any response to come back. By the time an answer arrived, the situation that prompted the question would be years in the past. The crew would have solved the problem, lived with the consequences, or perished, long before mission control on Earth even knew anything had gone wrong. This is not a detail. It is a fundamental restructuring of what a space mission means and how it operates. Every crewed mission in human history, from the earliest Mercury flights to the longest space station expeditions, has functioned within a framework of continuous communication with the ground. Flight controllers monitor telemetry in real time. Engineers on the ground analyze problems and uplink solutions. Medical teams track crew health and intervene when needed. The crew, for all their extraordinary skill and training, has always had Earth at their backs. An army of expertise, accumulated knowledge, and computational power available at the speed of a radio signal. Strip that away entirely, and you are left with something qualitatively different. An interstellar crew would need to carry not just the knowledge but the full decision-making capacity of every expert discipline that might be relevant to their survival. Medicine, engineering, agriculture, psychology, materials science, computer systems, biology, chemistry, navigation, and apply that knowledge autonomously without any possibility of outside consultation across a journey of decades. The crew cannot simply be excellent astronauts. They would need to be collectively a civilization in miniature, self-sufficient in every domain that matters, across every timescale that the mission spans. The training requirements alone are staggering to contemplate, and beyond training, there is the problem of knowledge itself evolving during the voyage. Imagine departing Earth in a given decade with the best medical knowledge available at that time. 50 years into the journey, medicine on Earth has advanced dramatically. New treatments exist for conditions that were previously fatal. New understanding of microbiology has transformed how infections are managed. New surgical techniques have been developed. The crew knows none of it. They are practicing the medicine of a previous era, not because they are negligent, but because the speed of light will not allow anything faster. The universe, indifferent as always, does not make exceptions. This communications isolation extends beyond practical problem-solving into something more personal and more difficult to quantify. Human beings are profoundly social. We derive meaning, stability, and identity from our connections to other people, to family, to friends, to the broader culture we grew up inside. An interstellar crew would watch those connections stretch across light years until they became something almost abstract. Messages from home would arrive years late, describing events and people as they were, not as they are. Children would grow up, parents would age and die, civilizations would change in ways both large and small, and the crew, suspended between the stars, would receive all of it delayed, filtered through the strange amber of travel time, unable to respond in any way that felt real or immediate. Some researchers who study the human dimensions of long-duration spaceflight have described this phenomenon as a kind of temporal orphaning, the gradual severing of a person's felt connection to the moment in time where their life began. It is distinct from ordinary homesickness, though it contains elements of that. It is more like watching your entire world become history while you are still alive to remember it. The psychological resilience required to absorb that experience without breaking, not just for one person but for every member of a crew, across decades, is something that no amount of terrestrial training can fully prepare anyone for, because nothing in terrestrial experience resembles it closely enough to serve as genuine preparation. And yet, and this is the part that fills me with a deep and complicated admiration for the human spirit, people have voluntarily endured extraordinary isolation for the sake of discovery throughout all of recorded history. Antarctic explorers in the early 20th century spent years cut off from civilization in conditions of physical hardship that modern readers find almost unimaginable. Submarine crews operate for months in enclosed metal tubes beneath the ocean, cut off from sunlight and fresh air and the open world. The crew of Apollo 8 became the first human beings to travel behind the moon, entering a zone of complete radio silence, cut off from every other human voice in existence on Christmas Eve of 1968, and they came back changed but intact, carrying with them one of the most famous photographs in history, Earthrise, our blue planet hanging over the lunar horizon, fragile and luminous and impossibly alone. The capacity for endurance is woven into us. What interstellar travel demands is not the invention of that capacity from scratch, but its extension to scale we have never previously attempted. That is a challenge, but it is a human challenge, which means it is, at least in principle, a solvable one. Now let us turn to a problem that is quieter than radiation, less visceral than bone loss, and in some ways more fundamental than all the others we have discussed. It is the problem of energy, specifically where a spacecraft bound for another star gets its power, and what happens when that power source ages, degrades, or fails. Every spacecraft we have ever launched has carried its energy with it or harvested it from the sun. Solar panels are the workhorse of modern space missions, converting sunlight into electricity with remarkable efficiency and reliability. The International Space Station's solar arrays generate roughly 215 kilowatts of power, enough to light approximately 40 average American homes. Many satellites and planetary probes rely on solar power almost exclusively. It is clean, renewable as long as the sun shines, and reasonably well understood from an engineering standpoint. But solar power has a hard limit built into physics itself. The intensity of sunlight falls off with the square of your distance from the sun. Double your distance, and you receive 1/4 the solar energy. Triple it, and you receive 1/9. By the time you reach Jupiter, roughly 5 times Earth's distance from the sun, solar panels receive only about 4% of the energy they would collect in Earth orbit. By the time you reach the outer edges of the heliosphere, where Voyager 1 crossed into interstellar space, the sun is so dim that solar power becomes essentially useless for anything beyond the most minimal applications. Deep space missions that need substantial power, like the Cassini spacecraft at Saturn or the New Horizons probe that gave us our first close look at Pluto in 2015, have historically relied on radioisotope thermoelectric generators, or RTGs. These devices generate electricity from the heat produced by the natural radioactive decay of plutonium-238. They are extraordinarily reliable. Voyager 1's RTGs are still producing usable power more than 4 decades after launch, though at reduced levels as the plutonium-238 decays, and they require no sunlight, no moving parts, and no external fuel source, but RTGs have serious limitations for a crewed interstellar mission. The power they produce is modest. Voyager 1's original RTGs produced roughly 470 watts at launch, enough to power a few household light bulbs. A crewed spacecraft needs orders of magnitude more than that to sustain life support, propulsion, communication systems, food production, medical equipment, and all the other systems that keep human beings alive and functional. Scaling RTGs up to the power levels required for a crewed vessel would demand quantities of plutonium-238 that do not exist in anything close to those amounts in any country's current inventory. The global production of the material is painstakingly slow, measured in kilograms per year, and rebooting production at meaningful scale would take decades and enormous investment, even if it were immediately prioritized. The most credible power source for a true interstellar mission, according to most serious analyses produced by aerospace engineers and physicists at institutions including NASA's Jet Propulsion Laboratory and various university research groups, is nuclear fission or fusion. Fission reactors, splitting heavy atomic nuclei to release energy, are proven technology. We have been running fission reactors on Earth since the 1940s, and the Soviet Union operated a series of fission-powered satellites throughout the Cold War. The United States has recently reinvested in space nuclear power through programs like the Killer Power project, which successfully tested a small fission reactor design in 2018. A sufficiently advanced fission reactor could potentially supply the power levels a crewed interstellar vessel needs, but bringing that technology to the reliability, compactness, and longevity required for a journey of decades is a formidable engineering challenge that remains well beyond our current capabilities. Fusion power, the same process that fuels the sun, fusing light atomic nuclei together to release enormous amounts of energy, is the ultimate dream. If we could build a compact, reliable fusion reactor, it would transform not just space travel but civilization on Earth. Fusion fuel, primarily isotopes of hydrogen, is effectively inexhaustible. The energy density is extraordinary. The waste products are far less problematic than those from fission. Researchers have been working toward practical fusion power since the 1950s, and meaningful progress has been made. The National Ignition Facility in California achieved fusion ignition in December 2022, producing more energy from fusion than the laser energy delivered to the fuel target, a landmark result that made headlines around the world. Private companies including Commonwealth Fusion Systems and TE Technologies are pursuing compact fusion reactor designs with serious funding and genuine scientific credibility. But there is a long distance between a laboratory demonstration and a reactor compact and reliable enough to power a spacecraft across the void between stars for decades without significant maintenance. That distance is measured not just in engineering milestones but in time, years and likely decades of development, testing, failure, refinement, and more testing. It is coming. The trajectory of the science suggests strongly that fusion power will eventually become practical, but it is not here yet, and an interstellar mission cannot wait for technology that does not exist. The energy problem, in the end, connects to something larger than just power generation. It connects to the fundamental question of how you sustain a closed system, a spacecraft, a crew, an ecosystem, across timescales that dwarf anything in our experience, using resources that are finite and cannot be replenished from outside. That question sits at the heart of interstellar survival, and it leads us directly to something that might be the most underappreciated challenge of all: the food problem human beings eat, constantly by cosmic standards. The average person requires roughly 2,000 calories per day just to maintain basic bodily function, more if they are performing the physical and cognitive labor that a spacecraft crew would demand. Over the course of a year, that is approximately 730,000 calories per person. For a crew of even 10 people on a 50-year journey, the total caloric requirement exceeds 365 million calories. Stored food, even the most calorie-dense, shelf-stable options available, cannot realistically supply that. The mass would be prohibitive, and the shelf life of stored food, even under ideal conditions, does not approach 50 years for most nutritionally complete options. The only viable solution is growing food aboard the spacecraft, not as a supplement to stored supplies, but as the primary food source. Agriculture in space, closed-loop food production systems that take water, light, carbon dioxide, and nutrient-rich growth medium and turn them into calories, vitamins, and everything else the human body needs to remain healthy across decades. NASA and research institutions around the world have been studying space agriculture seriously for decades, and meaningful progress has been made. Astronauts aboard the International Space Station have grown and consumed lettuce, radishes, and other leafy greens through experiments like the Veggie program and the Advanced Plant Habitat. These are encouraging demonstrations, but the gap between growing salad greens in a small growth chamber aboard a space station and sustaining the full caloric and nutritional needs of a crew entirely through onboard agriculture is vast, and crossing it involves challenges in plant biology, soil microbiology, lighting, water cycling, and atmospheric management that remain genuinely unsolved at the scales required. The universe does not give anything away for free. Every answer reveals new questions. Every solution introduces new complications. That is not a reason for despair. It is the very thing that makes the pursuit worthwhile. Let us step back for a moment and look at the full picture we have been building together. Radiation that quietly dismantles your DNA. A near-perfect vacuum that is somehow still dangerous enough to sandblast your hull into dust. Temperatures hovering just above absolute zero on one side of your ship while the other side bakes. Bones thinning in silence, muscles fading, eyes changing in ways medicine cannot yet fully reverse. A communications blackout so profound that the word isolation does not begin to cover it. Power systems that have never been tested at the timescales required. Food production challenges that remain unsolved at the necessary scale, and all of it happening simultaneously, compounding on each other, across a journey measured not in months, but in decades or generations. It would be easy, sitting with all of that, to conclude that interstellar travel is simply impossible, that the universe has drawn a line around our solar system and made it clear that we are meant to stay inside it. But that conclusion, tempting as it might feel, misreads both the history of science and the nature of the challenges themselves, because every single obstacle we have discussed is a physical problem. And physical problems, given sufficient ingenuity, time, and the peculiar, relentless creativity that seems to be humanity's most defining characteristic, have a way of eventually yielding to solutions. What we are really talking about when we talk about the barriers to interstellar survival is a roadmap, an extraordinarily demanding, humbling, and in places genuinely frightening roadmap, but a roadmap nonetheless. And today, right now, in laboratories and research institutions and conceptual design offices scattered across the planet, people are working on pieces of it, not all at once, not with the coordinated urgency that a true interstellar program would require, but working nonetheless, building the foundation. Let us talk about some of those efforts, because the story of interstellar survival is not only a story of obstacles, it is also increasingly a story of ingenuity meeting those obstacles with something approaching confidence. The radiation problem, for instance, is being attacked from multiple directions simultaneously. One of the most promising approaches involves not shielding at all, in the traditional sense, but biology. Specifically, the biology of extraordinarily radiation-resistant organisms. The tardigrade, a microscopic animal sometimes called a water bear, capable of surviving conditions that would kill virtually every other known organism, including exposure to the vacuum of space and doses of radiation that would be instantly lethal to a human being, has become a subject of intense scientific interest. Researchers have identified specific proteins in tardigrades, particularly one called D-sup, short for damage suppressor protein, that physically shields DNA from radiation-induced breaks. Studies published in journals including Nature Communications have shown that when the gene encoding DSP is introduced into human cells in laboratory conditions, those cells show significantly greater resistance to X-ray radiation than unmodified human cells. This is not science fiction. This is peer-reviewed biology happening right now. The leap from a laboratory result with human cells to a living human being with meaningfully enhanced radiation resistance is enormous. The ethical, medical, and technical challenges of genetic modification at that scale are profound, but the principle is established. The universe has already solved the radiation problem in at least one organism. The question is whether we can learn from that solution and apply it to ourselves. Alongside biological approaches, material scientists are developing new classes of radiation shielding that go beyond the simple mass-based protection of traditional lead or water shielding. Hydrogen-rich polymers, boron-containing compounds, and multi-layer composite materials designed to absorb and scatter different types of radiation across different energy ranges are all active areas of research. Groups at institutions including the Massachusetts Institute of Technology, Stanford University, and the German Aerospace Center have published work on novel shielding architectures that could provide substantially better protection per unit of mass than anything currently in use. The active magnetic shielding concept, creating an artificial magnetosphere around a crude spacecraft using superconducting electromagnets, has also advanced meaningfully from pure theory towards something approaching engineering feasibility. The European Space Agency funded a research project called SR2S, standing for Superconducting Shield for the Protection of Astronauts in Space, which ran from 2013 to 2015 and produced detailed technical assessments of what a practical magnetic shield system would look like. The conclusion was that it was not physically impossible, just enormously demanding in terms of the superconducting wire required, the cryogenic cooling systems needed to keep that wire functional, and the structural engineering required to mount it on a spacecraft. Demanding, but not beyond the reach of determined engineering, given sufficient development time. The microgravity problem is being approached through a combination of pharmaceutical interventions, advanced exercise countermeasures, and increasingly serious engineering work on rotating habitat designs. A group of researchers associated with MIT's Man Vehicle Laboratory has spent decades refining the engineering parameters for artificial gravity systems, working to identify rotation rates and radii that provide meaningful gravitational simulation while keeping Coriolis-induced disorientation within tolerable limits. Their findings suggest that a short-radius centrifuge, a rotating arm perhaps 10 to 20 meters long, used for a portion of each day rather than continuously, could provide significant bone and muscle maintenance benefits without requiring the construction of a massive rotating ring structure. It is a compromise, not a complete solution, but it represents the kind of pragmatic engineering thinking that turns theoretical concepts into buildable hardware. On the food production front, advances in controlled environment agriculture, a field driven largely by terrestrial applications like vertical farming and year-round crop production in northern climates, are generating technologies directly applicable to space agriculture. LED lighting systems tuned to the precise wavelengths that maximize plant growth efficiency. Hydroponic and aeroponic growth systems that use a fraction of the water required by soil-based agriculture. Closed-loop nutrient cycling that recaptures and reprocesses plant waste back into growth medium. Selective breeding and genetic optimization of crop varieties for high yield, compact growth habit, rapid maturation, and dense nutritional profiles. The research group at the University of Arizona's Controlled Environment Agriculture Center has been collaborating with NASA for years on exactly these problems, developing crop systems designed specifically for the constraints of long-duration spaceflight. Meanwhile, the broader vertical farming industry, companies like AeroFarms, Bowery Farming, and Plenty, is generating enormous amounts of practical engineering knowledge about growing food at scale in controlled environments, knowledge that translates directly to the spacecraft context even when that is not the primary motivation. There is also an entirely different philosophical approach to the survival problem that deserves serious consideration, one that sidesteps many of the biological challenges by rethinking who or what makes the journey in the first place. The generation ship concept has been a staple of science fiction for nearly a century, appearing in works from Robert Heinlein's Universe in 1941 to the television series The Expanse. The idea is straightforward in principle. Build a spacecraft large enough and self-sufficient enough to function as a complete, closed civilization. Launch it with an initial crew. Those people live out their lives aboard the vessel. Their children are born into it, their children's children. Generation after generation, the ship travels through interstellar space, maintained and guided by a succession of crews who were born to the mission and will die before its completion. After perhaps dozens of generations, the descendants of the original crew arrive at the destination, strangers to Earth, native to the ship, inheriting a goal set by ancestors they know only from history. The engineering requirements of a generation ship are almost incomprehensibly vast. You are not designing a spacecraft, you are designing a world, a biosphere, a society, an economy, a culture robust enough to maintain itself and its mission across centuries without the benefit of external input or correction. The minimum viable population required to maintain genetic diversity across multiple generations without dangerous inbreeding is a subject of genuine scientific study. Estimates from population geneticists vary, but figures in the range of several hundred to several thousand individuals appear frequently in the literature. A ship carrying that many people, with the agricultural systems to feed them, the medical infrastructure to care for them, the living spaces to house them with enough variety and richness to support psychological health across generations. Such a vessel would be extraordinary in scale. And then there is the social problem, which may be the generation ship's deepest challenge. How do you maintain a crew's commitment to a mission that none of them chose and that none of them will live to complete? How do you govern a closed society across centuries without the external checks and balances that terrestrial civilizations rely on? How do you prevent the kind of social fragmentation, ideological drift, and institutional decay that history tells us will inevitably affect any human community over long periods of time? These questions do not have engineering answers. They have sociological, philosophical, and political ones. And our track record with those kinds of questions, on Earth where the stakes are considerably lower, is decidedly mixed. The philosopher and sociologist Cameron Smith at Portland State University has done some of the most detailed academic work on generation ship population dynamics and social sustainability, publishing analyses of minimum crew sizes, genetic diversity requirements, and the cultural mechanisms that might maintain mission coherence across generations. His work is serious, rigorous, and genuinely valuable, and it also makes clear just how much we do not yet understand about how to design a society that can survive in isolation for centuries while retaining both its humanity and its purpose. A different approach that avoids the generational problem entirely is the concept of human hibernation, or more precisely, induced torpor. Rather than filling a spacecraft with an active, aging, eating, breathing, psychologically complex population for the duration of the journey, put the crew into a state of drastically reduced biological activity, lower their body temperature, slow their metabolism, keep them alive but suspended, aging far more slowly than they would in a normal waking state, consuming minimal resources until the ship approaches its destination and they are brought back to full consciousness. Hibernation of this kind does not exist in human medicine today, but it is not purely fictional either. The phenomenon of mammalian hibernation is well understood at a biological level. Bears, ground squirrels, and numerous other species dramatically reduce their metabolic rate and body temperature during winter, surviving for months in a state of suspended animation that shares important physiological features with what a spacecraft torpor system would need to achieve. And human beings can and do experience states of reduced metabolic activity under certain medical conditions. Patients cooled to low body temperatures during certain cardiac and neurological surgeries have survived periods of dramatically reduced brain and body activity that would not be possible at normal temperatures. A company called SpaceWorks Enterprises, which has consulted with NASA on long-duration mission concepts, has published detailed engineering analyses of what they call a torpor-inducing transfer habitat, a spacecraft module designed to keep a crew of astronauts in a hibernation-like state for the duration of a journey to Mars. Their analyses suggest that such a system could dramatically reduce the mass required for crew consumables, shrink the required habitat volume, and reduce the psychological toll of long-duration isolation. They acknowledge that the medical technology to safely induce and reverse human torpor does not yet fully exist, but they argue that the gap between current medical capability and what would be needed is smaller than it might appear, and that targeted research investment could close it within decades. Whether they are right about that timeline is something only time itself will answer. But the concept points towards something important. The most significant barriers to interstellar survival are not necessarily the ones that seem most dramatic from the outside. Radiation and distance capture the imagination. But the quieter challenges, keeping human bodies functional, human minds coherent, and human societies purposeful across the crushing expanse of interstellar time, may ultimately prove to be the ones that determine whether we ever truly become a species that reaches beyond our own star. And there is one more layer to this story, one that sits beneath all the engineering and medicine and sociology and physics. It is the layer of meaning, the question of why, because in the end, the decision to attempt interstellar travel, to commit the resources, the ingenuity, and the lives that such an attempt would require, is not a scientific decision. It is a philosophical one. It is a statement about what we believe we are, what we believe we owe to the future, and what we think the universe is for. Carl Sagan, whose thinking about the cosmos remains as alive and relevant today as it was during his lifetime, wrote in his book Pale Blue Dot, published in 1994, that the Earth is a very small stage in a vast cosmic arena. He was writing in response to the famous photograph taken by Voyager 1 in 1990, at his request, showing Earth as a tiny, barely visible speck suspended in a beam of sunlight against the darkness of space. That photograph, that pale blue dot, is perhaps the most powerful image ever taken, not for what it shows, but for what it implies. That everything we have ever known, every war ever fought, every triumph ever celebrated, every life ever lived, happened on that infinitesimal point of light. Sagan's response to that humbling realization was not despair, it was urgency, an urgency to extend what we are, curious, creative, loving, flawed, extraordinary, beyond the fragile surface of a single world, to become, as he put it, a spacefaring species, not because space is comfortable or easy or safe, but because the alternative is to leave all our eggs in one basket. Because the universe is old and occasionally violent, and the history of Earth is punctuated by catastrophes that remind us periodically and brutally that no world is permanent, that urgency is still there. If anything, it has grown. We know more now than Sagan did about the fragility of planetary ecosystems, about the long-term threats posed by asteroid impacts, supervolcanic eruptions, and the slow brightening of our sun over geological time. We know more about the diversity of worlds in our galaxy, thousands of confirmed exoplanets, many of them potentially habitable, discovered by missions like Kepler and the Transiting Exoplanet Survey satellite, known as TESS. We know that the raw material for life, the chemistry that underlies everything we are, is scattered throughout the galaxy in molecular clouds and on the surfaces of asteroids and in the organic chemistry of distant star systems. The universe, in other words, has been generous with its ingredients. It has placed the building blocks of complexity everywhere we look. What it has not done is make the journey between those places easy. That is our problem to solve. And the fact that the problem is so enormously difficult is not a discouragement. It is an invitation. Let us talk about something that almost never makes it into the popular conversation about interstellar travel, something that sits quietly in the background of every mission concept ever seriously proposed, waiting to be acknowledged. It is the problem of the destination itself, because in all the focus on the journey, the radiation, the distance, the engineering, the human cost, it is easy to forget that arriving somewhere does not mean arriving somewhere safe. It does not mean arriving somewhere known. And it certainly does not mean arriving somewhere that will welcome you. When we point our telescopes at nearby star systems and search for potentially habitable worlds, we are working with instruments of extraordinary sophistication and sensitivity. The Kepler Space Telescope, which operated from 2009 to 2018, detected more than 2,700 confirmed exoplanets by measuring the tiny dimming of starlight as a planet passed in front of its host star. Its successor, the Transiting Exoplanet Survey satellite, TESS, launched in 2018, and has continued building that catalogue, identifying thousands more candidate worlds. The James Webb Space Telescope, which began science operations in 2022 and represents perhaps the most powerful astronomical instrument our species has ever constructed, has begun analyzing the atmospheres of some of these worlds with a precision that was unimaginable just a decade ago. And yet, for all that power, all that sensitivity, all that accumulated ingenuity, we cannot tell you with certainty what is actually on the surface of any of these worlds. We can measure their size, we can estimate their mass, we can analyze the starlight filtered through their atmospheres and identify certain chemical signatures: water vapor, carbon dioxide, methane, oxygen, that hint at conditions potentially favorable to life as we understand it. But the gap between those measurements and a genuine detailed knowledge of what a crew would find upon arrival is immense. Consider the most discussed nearby candidate, Proxima Centauri b, discovered in 2016 and confirmed through subsequent observations. It is a planet orbiting Proxima Centauri, the closest individual star to our Sun, sitting at approximately 4.2 light-years from Earth and part of the Alpha Centauri system. Proxima b orbits within what astronomers call the habitable zone of its star, the region where liquid water could theoretically exist on a planetary surface. That single fact has generated enormous excitement in the planetary science community, and understandably so, but the more carefully you look at Proxima b, the more complicated the picture becomes. Proxima Centauri is not a star like our Sun. It is an M-dwarf, a red dwarf star considerably smaller, cooler and dimmer than the Sun, which is why a planet needs to orbit so close to it to receive enough warmth to potentially support liquid water. That close orbit creates problems. Proxima b completes a full orbit in approximately 11 Earth days. At that distance, gravitational tidal forces from the star are likely strong enough to have locked the planet into synchronous rotation, meaning the same side of the planet always faces the star. Just as the same side of the Moon always faces Earth, one hemisphere bakes under a perpetual sun, the other freezes in permanent darkness. Whether the atmospheric circulation patterns on such a world could redistribute heat effectively enough to create habitable conditions across the surface is a question that planetary scientists debate actively without a definitive answer, and that is before we get to the radiation environment. Proxima Centauri is a flare star, spectacularly, violently active compared to our relatively stable Sun. It produces intense ultraviolet and X-ray flares with a frequency and magnitude that would, on a world without a substantial protective magnetic field and atmosphere, strip away the surface conditions favorable to life with brutal efficiency. In 2019, astronomers using the Atacama Large Millimeter Array detected a superflare from Proxima Centauri, roughly 1,000 times more energetic than the largest solar flare ever recorded from our own Sun. If Proxima b lacks a strong magnetic field, which is entirely possible, given the uncertainties in our current models of planetary magnetic field generation, then its surface may be exposed to radiation levels that would challenge even the hardiest extremophile organisms on Earth. None of this definitively rules out the possibility of life on Proxima b. Science rarely works in definitive rulings, but it paints a picture considerably more complicated and potentially hostile than the simple phrase habitable zone planet implies. And it serves as a reminder that an interstellar crew arriving at Proxima Centauri after decades of travel would not be stepping off their ship onto a world that any telescope on Earth had given them a genuinely complete picture of. They would be arriving at a place full of unknowns, some of them pleasant, some of them manageable, and some of them potentially catastrophic. How do you prepare for unknowns you cannot characterize from 4 light-years away? How do you design life support systems, protective equipment, and contingency plans for surface conditions you cannot fully measure until you are already there? The history of exploration on Earth offers some guidance. The great maritime explorers of the 15th and 16th centuries set sail for destinations they understood only partially, relying on general knowledge, preparation for a range of possible conditions, and the kind of adaptive thinking that only experience can teach. But those explorers could turn around. They could modify their plans, return to port, gather more information, and try again. An interstellar crew has none of those options available. The scenario becomes even more complex when you consider the possibility, remote, uncertain, but scientifically non-trivial, of finding life at the destination. Not intelligent life necessarily, microbial life, the kind of simple, chemically driven biological activity that dominated Earth for the first 3 billion years of its history, and that, given the ubiquity of organic chemistry across the galaxy, some scientists believe may not be rare at all. The discovery of even microbial life at another star system would be arguably the most significant scientific finding in human history, a transformation of our understanding of what the universe is and what our place within it means. But that discovery would also create an immediate and profound ethical problem, because life, even microbial life, represents an independent biological heritage, an ecosystem, however simple, a chemistry that has been developing in its own direction for potentially billions of years. And a crewed spacecraft arriving in that system carries with it, inevitably, inescapably, the biological heritage of Earth. Human beings, even in the cleanest spacecraft ever designed, shed cells, they exhale gases, they carry microorganisms on every surface of their bodies and throughout their digestive systems. The idea of biological contamination, of Earth life reaching and potentially disrupting or destroying an alien biological system, is taken extremely seriously by planetary protection scientists right now. Even within our own solar system, NASA's planetary protection policies govern every mission sent to bodies in our solar system that might harbor life, including Mars, Europa, and Enceladus. Spacecraft are built in clean rooms, components are sterilized, procedures are followed with extraordinary care, and still, complete biological sterility is essentially impossible to achieve. Sending human beings, the most biologically complex and microbiologically rich objects we could possibly introduce into an alien environment, to a world that might harbor its own life, raises ethical questions of a depth and complexity that no current framework adequately addresses. Do we have the right to potentially contaminate another world's biology? Does our desire to explore, to expand, to survive as a species outweigh the potential harm to whatever might already be living at our destination? And conversely, what does the biology of that destination do to us? An alien microbial ecosystem, evolved entirely independently of Earth life, might produce chemical compounds, metabolic byproducts, or structural features that interact with human biology in ways we cannot predict and cannot prepare for. The immune system that has evolved over millions of years to recognize and respond to Earth-derived pathogens would have no frame of reference for something genuinely alien. The potential consequences of that encounter range from completely benign to genuinely catastrophic, and we would have no way of knowing in advance which end of that spectrum we were walking toward. These are not hypothetical concerns invented for dramatic effect. They are real questions being debated right now by astrobiologists, bioethicists, and planetary scientists at institutions around the world. The astrobiology community, researchers like Sarah Seeger at MIT, David Grinspoon at the Planetary Science Institute, and the teams working with data from the James Webb Space Telescope, is grappling seriously with the question of what it would mean to find life elsewhere and how that finding should reshape our approach to exploration. Their conversations are rigorous, thoughtful, and increasingly urgent as our detection capabilities improve and the list of potentially habitable worlds grows. There is also a navigational dimension to the destination problem that deserves attention because it is technically demanding in ways that are easy to underestimate. Pointing a spacecraft at a star 4 light-years away and keeping it on course across a journey of decades is not simply a matter of aim and fire. Stars move. Not dramatically by human standards, the proper motion of Proxima Centauri relative to our Sun is only about 3.85 seconds of arc per year, but across a journey of 20, 30, or 50 years, that motion adds up. A spacecraft launched today aimed at where Proxima Centauri is today would not be aimed at where Proxima Centauri will be when it arrives. Navigation for an interstellar mission requires calculating and accounting for the star's motion over the full duration of the journey and then making corrections along the way as measurements improve and accumulated errors are detected. Those corrections require propulsion, the ability to make controlled adjustments to the spacecraft's trajectory over the course of decades, and propulsion in interstellar space is not like propulsion near Earth, where mission controllers can calculate a burn, uplink the commands, and have the spacecraft execute them in something close to real time. On an interstellar trajectory, the crew, or the spacecraft's autonomous systems, if the crew is in hibernation, must be capable of performing complex navigational calculations and executing precise maneuvers without any real-time guidance from Earth. The software and hardware required for that level of autonomous navigation over multi-decade timescales represents a significant unsolved engineering challenge, particularly given the radiation environment that will be working constantly to degrade and corrupt electronic systems throughout the journey. Some mission concepts address this through the use of pulsars as navigational beacons, extraordinarily regular rotating neutron stars that emit beams of radio waves with a timing precision that rivals the best atomic clocks on Earth. By measuring the arrival times of pulsar signals from multiple known pulsars, a spacecraft's computer can triangulate its position in the galaxy with remarkable accuracy, independent of any communication with Earth. This technique, sometimes called pulsar navigation or X-ray navigation, has been tested aboard the International Space Station through an experiment called NISA, the Neutron Star Interior Composition Explorer, which demonstrated in 2018 that autonomous spacecraft navigation using pulsar timing signals is technically feasible. It is one of those quietly elegant solutions that feels, once you understand it, almost like the universe leaving breadcrumbs. But breadcrumbs only help if you can follow them, and following them requires systems, detectors, computers, power supplies, structural mounts that continue functioning accurately across the full duration of a multi-decade journey in one of the most hostile environments imaginable. Every solution in interstellar engineering comes with its own set of requirements, and those requirements circle back to the same fundamental challenges: power, reliability, radiation hardness, and time. What strikes me most, sitting with all of this, is not the magnitude of the obstacles. It is the fact that so many of the solutions are already visible on the horizon. They are not here yet. They require development, investment, testing, and time, but they are not miracles. They are engineering. They are biology. They are physics operating exactly as physics always operates, consistently, mathematically, without prejudice toward the people trying to understand it. The universe is not trying to stop us. It simply is what it is: vast, ancient, indifferent, and in places extraordinarily hostile to the kind of fragile, warm, water-dependent, oxygen-breathing creatures that evolved on the surface of a small rocky planet in an unremarkable corner of the Milky Way. We were not designed for it. We were designed by it, forged in the nuclear furnaces of stars that lived and died before the sun was born, assembled by 4 billion years of evolutionary experimentation on a world that was itself shaped by cosmic forces of unimaginable scale. We are made of the same stuff as everything out there. The iron in your blood was forged in a dying star. The calcium in your bones was scattered across space by a supernova explosion billions of years before Earth existed. The water in every cell of your body has been cycling through the cosmos for longer than our solar system has been alive. In the most literal, physical, chemical sense, you are already interstellar. The journey, in a way, is just coming home. That does not make it easy, but it makes it meaningful in a way that goes beyond mission objectives and scientific discovery and the practical necessity of species survival. It makes it a story about the universe becoming aware of itself, about the matter and energy that have been moving through the cosmos since the beginning of time, organizing itself over billions of years into something curious enough, creative enough, and perhaps brave enough to turn around and look back at where it came from. There is a question that tends to surface whenever serious people sit down to discuss interstellar travel, and it is a question that cuts through all the engineering and biology and physics with the clean precision of something that does not have a technical answer. It is simply this: even if we could solve every problem we have discussed, the radiation, the microgravity, the power, the food, the communications blackout, the destination uncertainties, even if we built the perfect ship and trained the perfect crew and launched with every conceivable advantage on our side, would the human mind survive the journey intact? Not the human body, the human mind, the part of us that makes us who we are, the part that needs meaning, needs purpose, needs connection, needs the feeling that what we are doing matters. This is not a soft question. It is not a philosophical luxury to be considered after the hard engineering problems are solved. It is, in the assessment of many researchers who have spent careers studying human performance in extreme environments, the central question. Because a spacecraft full of physically healthy but psychologically broken human beings is not a spacecraft that completes its mission. It is a tragedy drifting through the dark. The psychology of isolation and confinement has been studied seriously since the early days of the space program, and what that research has accumulated over decades is a picture of remarkable nuance and sobering complexity. Human beings are adaptable, extraordinarily so. The documented capacity of individuals and groups to endure conditions that seem, from the outside, humanly unbearable is one of the most consistently surprising findings in the psychology of extreme environments. People survive, they find meaning, they build community, they discover reserves of patience and creativity and mutual support that they did not know they possessed until circumstances demanded them. But adaptation has limits, and those limits reveal themselves not at the beginning of an ordeal, when motivation is high and the novelty of the situation provides a kind of psychological cushion, but in the middle, in what researchers who study long-duration Antarctic expeditions and submarine deployments and extended space missions call the third quarter phenomenon. Roughly 3/4 of the way through any long, isolated, confined mission, something predictable happens. Morale drops, interpersonal friction escalates, motivation falters. The end feels both tantalizingly close and still impossibly far away, and the accumulated psychological weight of everything that came before, the monotony, the close quarters, the small irritations that become enormous over time, the grief of everything left behind, bears down with a force that the opening weeks of the mission did not prepare anyone for. On a mission to Mars, the third quarter might arrive after about a year and a half, difficult but survivable with appropriate psychological support systems in place. On an interstellar voyage lasting 50 years, the third quarter arrives after 37 and a half years. A crew member who was 25 years old at launch would be 62 years old, with roughly 12 and a half years still remaining before arrival. They would have spent the majority of their entire adult life aboard the vessel. Whatever they left behind on Earth, family, friends, a world they grew up in, would be gone or transformed beyond recognition. The destination would still be years away, and everything they had endured to that point would be the context inside which they were trying to find the psychological resources to endure what remained. This is the part that no mission briefing can fully convey to a volunteer before departure, not because the information is unavailable, but because human beings are not wired to emotionally internalize the weight of experiences they have not yet had. You can tell someone that 35 years of confinement will be heavy. You cannot make them feel the weight of it before they have carried it. And once they are carrying it, 4 light years from the nearest other human civilization, there is no putting it down. Researchers at institutions, including the Institute for Biomedical Problems in Moscow, which has conducted some of the world's most extensive analog mission simulations, including the Mars 500 project, have identified several factors that consistently distinguish crews that manage isolation well from those that deteriorate. A shared sense of purpose is near the top of every list. The conviction that what the group is doing matters, that the mission has meaning beyond the individual members, that the sacrifice is in service of something genuinely worth the cost. This appears to be one of the most powerful psychological stabilizers available to an isolated crew. It does not eliminate hardship. It contextualizes it. It gives the hardship a frame inside which it becomes endurable rather than merely pointless. For an interstellar crew, that shared sense of purpose would need to be maintained not for months but for decades. Across the natural human cycles of enthusiasm and exhaustion, faith and doubt, connection and estrangement, across the loss of crew members to illness or accident, or the simple mortality that no spacecraft can prevent, across the births of children who chose none of this but inherit all of it. Building a mission culture robust enough to sustain that sense of purpose across those timescales is arguably the most complex social engineering challenge in the history of our species. It makes the construction of stable, long-lived civilizations on Earth look straightforward by comparison, and we know, from the long and turbulent record of human history, that building stable, long-lived civilizations is anything but straightforward. There is a school of thought, growing in credibility among some researchers, that the answer to the psychological challenge of interstellar travel lies not in trying to maintain human psychology in its current form across the journey, but in rethinking the structure of the mission around what human beings actually need, rather than trying to force human beings to function in conditions they were not shaped for. This approach argues that a successful interstellar mission would need to be, in a very real sense, a complete human world, not a military operation or a scientific expedition, but a community, a society, a place where people live full lives, not just endure a crossing. That means art. It means music and storytelling and celebration, and grief and romance and conflict resolution, and all the other dimensions of human social life that get quietly stripped away when we imagine spaceflight as a purely functional endeavor. An interstellar vessel designed along these lines would devote significant volume and resources not to redundant engineering systems, but to the things that make human life feel worth living: spaces for gathering, for privacy, for creativity, for the cultivation of the interior life that every person needs to remain recognizably themselves across time. The architect and designer Konstantin Tsiolkovsky, the Russian pioneer of astronautics, whose theoretical work in the late 19th and early 20th century laid the conceptual foundations for modern rocketry, wrote that Earth is the cradle of humanity, but one cannot live in a cradle forever. He was thinking about the physical act of leaving the planet, but the metaphor extends further than he perhaps intended. The cradle is also the familiar, the comfortable, the known, growing beyond it, truly, permanently, across the most extreme distances the cosmos offers, requires not just better engines but a deeper and more honest reckoning with what we are, what we need, and what we are willing to build for the sake of a future we will never personally inhabit. Let us turn now to something that has been lurking at the edges of our conversation throughout, something that the most technically minded discussions of interstellar travel tend to treat as a distant concern, but that the physics insists on placing at the center of any honest accounting. It is the problem of propulsion. Not because we have not discussed it at all. We have touched on it in the context of breakthrough starshot and the general challenge of crossing interstellar distances in reasonable timeframes, but because the propulsion problem is so fundamental and so deeply connected to every other challenge we have explored that it deserves its own careful examination, here is the core issue, stated as simply as possible. To reach Alpha Centauri in a time frame meaningful to a human crew, say within a single lifetime of perhaps 70 or 80 years, you need to travel at a significant fraction of the speed of light. Even at 10% the speed of light, the journey would take about 42 years. At 20%, roughly 21 years. Those numbers start to feel manageable, at least in principle. But achieving even 1% the speed of light, which equals roughly 3,000 kilometers per second, requires an amount of energy that dwarfs anything we have ever generated or stored in the history of our civilization. The rocket equation, derived by Tsiolkovsky himself in 1897, tells us something deeply inconvenient about conventional chemical propulsion. The faster you want to go, the more propellant you need. But the more propellant you carry, the heavier your spacecraft becomes. And the heavier your spacecraft, the more propellant you need to accelerate it. This feedback loop, called the tyranny of the rocket equation in aerospace engineering circles, means that conventional chemical rockets, the kind that have carried every human being who has ever left Earth, cannot get anywhere close to the velocities required for interstellar travel in any practical time frame. The energy simply is not there in chemical bonds. Nuclear propulsion offers a dramatic improvement. A nuclear thermal rocket, which heats propellant using a nuclear reactor rather than chemical combustion, can achieve exhaust velocities roughly twice those of the best chemical engines currently in operation. The nuclear pulse propulsion concept, formerly studied under the classified Project Orion in the United States from 1958 to 1965, proposed propelling a spacecraft by detonating a series of nuclear bombs behind a massive pusher plate. Theoretical analyses suggested that an Orion-type vehicle could achieve velocities of perhaps 3 to 5% the speed of light, enough to reach Alpha Centauri in roughly 100 years. Extraordinary by any conventional standard, but still generationally demanding, and the concept requires carrying aboard a spacecraft the equivalent of a city-destroying nuclear arsenal, which creates its own somewhat obvious set of safety concerns. If you are enjoying this journey, make sure to subscribe to the channel. You will be part of a community that explores the cosmos together. More advanced concepts go further. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, imagined a spacecraft with an enormous electromagnetic scoop hundreds of kilometers across, collecting interstellar hydrogen as it traveled and feeding it into a fusion reactor as propellant. The beauty of the concept is that it would not need to carry its fuel at all. It would harvest it from the interstellar medium itself, solving the propellant mass problem elegantly. Subsequent analysis has unfortunately revealed serious physical obstacles. The interstellar medium is too sparse to supply sufficient fuel at realistic speeds, and the magnetic scoop would create more drag than thrust under realistic conditions. But the creative spirit of the concept, the idea of living off the cosmic environment rather than carrying everything from home, points toward a way of thinking about interstellar engineering that remains genuinely productive. Laser propulsion, the technology underlying breakthrough Starshot, sidesteps the propellant problem entirely using a powerful ground-based laser array to push a lightweight sail, leaving all the energy generation equipment at home and sending only the spacecraft itself. For tiny probes, this approach is theoretically capable of achieving the velocities needed for interstellar transit within a reasonable time frame. The engineering challenges are formidable. Building a laser array powerful enough to accelerate even a small spacecraft to 20% the speed of light would require a facility of extraordinary scale, and pointing that laser with sufficient precision at a target receding at those velocities across vast distances is technically demanding in ways that push current engineering to its absolute limits. But the physics work. The concept does not violate any known law of nature. For a crewed mission, though, laser propulsion faces an immediate and apparently insurmountable problem. The laser pushes the ship away from Earth, but there is no laser at the destination to slow it down. A spacecraft arriving at Alpha Centauri at 20% the speed of light with no way to decelerate would not enter orbit around any planet or stop to investigate anything. It would streak through the system in hours and continue into the void beyond, its mission over before it began. Deceleration is, in some ways, an even harder problem than acceleration. because by the time you need to slow down, you are 4 light-years from any infrastructure that could help you do it. Some proposals address this by splitting the mission into 2 phases, accelerating using a laser array at Earth, then decelerating using a smaller laser array at the destination, perhaps constructed and positioned by robotic precursor missions launched decades before the crewed voyage. Others propose using the stellar wind and magnetic field of the destination star as a braking mechanism, a kind of cosmic parachute deployed as the spacecraft approaches. Others still return to the idea of onboard propellant for deceleration, accepting the mass penalty while using the laser for initial acceleration to minimize the total propellant required. None of these solutions is clean. All of them require technologies beyond our current state of development, though none requires violating any fundamental physical principle. They are engineering challenges, not impossibilities. And that distinction, as we have returned to again and again throughout this conversation, is the most important one we can draw, because at the bottom of every challenge we have discussed, the radiation, the microgravity, the power, the food, the psychology, the communications, the destination uncertainty, the propulsion, at the bottom of all of it sits not a wall but a problem, and problems, in the hands of a species that taught itself to fly in 1 century and walked on the moon in the next, have a way of becoming solutions. We are early, profoundly, almost embarrassingly early in our development as a spacefaring species. Voyager 1, our most distant emissary, has traveled for nearly 50 years and covered barely 1/500th of the distance to the nearest star. In cosmic terms, we have not yet left the driveway. The engineering and science required for true interstellar travel belong to a civilization perhaps 100, perhaps 500, perhaps 1,000 years more advanced than we are today. A civilization that we are right now in the very earliest stages of becoming. That perspective is not discouraging. It is clarifying. It tells us that the work happening today, the radiation biology research, the advanced materials development, the nuclear propulsion programs, the space agriculture experiments, the fusion energy breakthroughs, the pulsar navigation demonstrations, is not preliminary to the real work. It is the real work. The foundation is being laid, 1 experiment, 1 paper, 1 breakthrough at a time, by researchers who understand that they will not live to see the destination, but who find the building worthwhile regardless. That is, when you think about it, one of the most deeply human things imaginable. We build cathedrals we will never see completed. We plant trees whose shade we will never sit in. We conduct research whose applications will emerge only after we are gone. The Interstellar project is the grandest expression of that impulse, the conviction that the future deserves our best effort, even when we will not be there, to share in its rewards. There is a concept in astrophysics called the cosmic perspective, and it is both the most disorienting and the most liberating idea that science has ever handed to a human being. It is the recognition, arrived at not through meditation or philosophy, but through the cold, precise machinery of measurement and mathematics, that the universe is so incomprehensibly large, so ancient, so indifferent to the concerns of any individual life or civilization, that our ordinary frameworks for understanding significance simply break down when applied to it. And yet, and this is the part that never stops striking me as extraordinary, within that incomprehensible vastness, on a small rocky world orbiting an unremarkable star in a spiral arm of a galaxy containing somewhere between 100 billion and 400 billion other stars, something happened. Chemistry became biology. Biology became consciousness. Consciousness became curiosity. And curiosity became the kind of creature that builds telescopes and launches probes and lies awake at night, wondering what is out there. That creature is you. That creature is us. And the fact that we exist at all, that the universe has, in at least one place we know of, organized itself into something capable of asking questions about its own nature, is perhaps the single most astonishing fact in the entire scientific inventory of what we know. I want to hold that thought for a moment before we continue, because it is directly relevant to something that does not get discussed enough in conversations about interstellar travel. We have spent considerable time in this exploration talking about the threats waiting in interstellar space, the radiation, the distances, the biological degradation, the engineering challenges, the psychological demands, and all of those threats are real. All of them deserve the serious attention we have given them. But there is another side to the interstellar story that is equally real, and, in its own way, equally staggering. It is the side that involves what we might learn, what we might find, what the act of genuinely reaching beyond our solar system, of becoming, for the first time in our history, a truly interstellar species, might do to our understanding of ourselves and our place in the cosmos. Consider what happened to our self-image the last time we took a major step outward. When the Apollo astronauts left Earth's orbit and traveled to the Moon, a journey that, in cosmic terms, is so small as to be essentially zero, a fraction of a millimeter on a map of the galaxy, the experience produced one of the most profound psychological and cultural shifts in modern history. Not because of the science, though the science was extraordinary, but because of the view, because for the first time, human beings looked back at their home planet from the outside and saw it whole, saw its fragility, saw its beauty, saw, with their own eyes, the truth that philosophy and science had been trying to communicate for centuries, that we share one world, one thin shell of air and water and life, suspended in an immensity that does not notice us. The Earthrise photograph, taken by astronaut William Anders during Apollo 8 on December 24, 1968, is credited by environmental historians with helping catalyze the modern environmental movement. The first Earth Day was held less than 2 years later, in April 1970. The connection is not coincidental. Seeing the Earth from the outside changed how people related to it, changed what they felt they owed it, changed the emotional texture of their responsibility toward it. Now imagine the equivalent shift that would accompany genuinely leaving our solar system, not photographing Earth from the Moon, but from 4 light-years away, a distance at which our entire solar system, Sun included, would be invisible to the naked eye and visible only as a faint point of light to a sensitive telescope. A distance at which the radio signals of our entire civilization, traveling outward in every direction since Guglielmo Marconi sent the first transatlantic radio transmission in 1901, would still not have reached the nearest star. A distance at which everything humanity has ever done, said, built, destroyed, created, and imagined exists in a sphere of radio waves still expanding outward through space, having not yet touched anything beyond our own star's gravitational influence. The crew of an interstellar spacecraft, looking back at that point of light, would be having an experience with no precedent in human history. Not even the Apollo astronauts, extraordinary as their journey was, traveled far enough to lose sight of the Earth entirely. An interstellar crew would. They would look back and see nothing. The dot would be gone. Their home, their species, their entire history, indistinguishable from the background field of stars. And they would need to carry that experience inside themselves, integrate it into their sense of identity and purpose, and continue functioning as a cohesive community with a mission to complete. What that experience does to a person, what it does to a group of people over years and decades of living with it, is something we genuinely do not know. It might be crushing, it might be transcendent, it might be both, in waves, cycling through an individual's inner life with the slow rhythm of a decades-long journey. Researchers who have studied the overview effect the well-documented cognitive and emotional shift experienced by astronauts who see the Earth from orbit believe that something profound and lasting happens when a person's visual and visceral experience of home is restructured by distance. The overview effect, as described by astronauts from Edgar Mitchell to Chris Hadfield to Ron Garan, consistently involves a feeling of deep interconnection, of boundaries dissolving, of the extraordinary preciousness of life becoming suddenly viscerally obvious rather than abstractly understood. If the overview effect from low Earth orbit produces that shift in perception, what might we call the experience of viewing your home star as an invisible point from 4 light-years away? We do not have a word for it yet. We have not needed one, but we may someday, if we are brave enough and patient enough and ingenious enough to get there. Now let us talk about something that has undergone a quiet revolution in the last 2 decades, something that directly shapes the scientific and emotional context of any interstellar mission we might eventually attempt. We are talking about exoplanet science, the study of planets orbiting other stars, and specifically about how rapidly and dramatically our knowledge in this field has expanded since the first confirmed detection of an exoplanet orbiting a Sun-like star in 1995. That discovery, made by Swiss astronomers Michel Mayor and Didier Queloz using the radial velocity method, detecting the tiny wobble a planet's gravity induces in its host star, was awarded the Nobel Prize in Physics in 2019, a recognition of just how fundamentally it reshaped our understanding of the universe. Before 1995, we had strong theoretical reasons to believe that planets around other stars were common, but no direct observational evidence. The discovery of 51 Pegasi b, a gas giant orbiting improbably close to its star, completing a full orbit in just over 4 days, shattered existing models of planetary formation and opened a new era in astronomy. In the 3 decades since, the pace of discovery has been extraordinary. The Kepler Space Telescope alone, during its 9 years of operation, demonstrated that planets are not rare exceptions in our galaxy, but are in fact extraordinarily common, with estimates based on Kepler data suggesting that virtually every star in the Milky Way hosts at least one planet, and that tens of billions of potentially rocky, potentially habitable worlds exist in our galaxy alone, tens of billions, in a galaxy of 100 to 400 billion stars. The numbers are almost too large to hold. The James Webb Space Telescope has added a new dimension to this picture by moving beyond simply detecting exoplanets to actually characterizing their atmospheres in detail. In 2023, Webb detected carbon dioxide and sulfur dioxide in the atmosphere of a planet called WASP-39b, a gas giant, not a habitable world, but a demonstration of the technique's power. In 2024, Webb produced detailed atmospheric spectra for several super-Earth candidates in or near habitable zones of their host stars, with results still being analyzed and debated in the scientific community. The telescope's sensitivity is such that, for nearby systems with favorable orbital geometries, it can detect the chemical fingerprints of specific molecules in planetary atmospheres from hundreds of light-years away. What Webb is ultimately searching for, what the entire exoplanet science community is building toward, is a biosignature, a chemical signal in a planetary atmosphere that cannot reasonably be explained by non-biological processes and that therefore constitutes evidence, however indirect, of life. Oxygen is one candidate because on Earth it is almost entirely produced by photosynthesis and would disappear from our atmosphere within a few million years if life stopped producing it. Methane in combination with oxygen is another, because the two react chemically and would quickly destroy each other in the absence of a continuous biological source replenishing both. Nitrous oxide, produced by certain microbial processes, has been proposed as a potentially more robust biosignature than oxygen alone. No confirmed biosignature has been detected yet. The search continues, and the significance of that search for any future interstellar mission is profound, because it means that by the time humanity is technologically capable of sending a crewed mission to another star, which most serious estimates place at least 100 years in the future, and possibly much longer, we will almost certainly have a dramatically clearer picture of what is actually at potential destinations. We will not be flying completely blind. We will be flying with the best atmospheric characterization data that centuries of increasingly powerful telescopes will have accumulated, a detailed reconnaissance of target worlds conducted at the speed of light, arriving long before any crewed mission could. That reconnaissance changes the nature of interstellar mission planning fundamentally. Instead of launching into pure uncertainty, future mission planners may be selecting among a short list of candidate worlds whose atmospheric compositions, temperature profiles, surface pressures, and possibly even seasonal variations are already reasonably well understood from remote observation. The decision of where to go, one of the most consequential choices any interstellar mission would face, may be informed by a century or more of telescopic observation that narrows the candidates from billions to dozens to perhaps a handful of worlds with genuinely compelling profiles. This is not guaranteed. The history of science is littered with cases where remote observation failed to reveal something critical about a target that direct investigation then uncovered. Mars, observed telescopically for centuries, was believed by serious scientists, including Percival Lowell, in the early 20th century to host a civilization of canal-building beings. Direct exploration revealed a cold, thin-atmosphered, radiation-baked desert. Europa, observed as a smooth, icy moon for decades, was only revealed by the Galileo spacecraft's magnetic field measurements in the late 1990s to almost certainly harbor a vast liquid water ocean beneath its frozen surface, an ocean containing more water than all of Earth's oceans combined, with genuine potential for harboring life. Raman observation is powerful. It is also incomplete. Whatever telescopes tell us about a target world 4 light-years away, there will be things that only direct investigation can reveal. That is not a flaw in the plan. It is, in fact, the point of going. There is something else happening right now in laboratories and research institutions around the world that is quietly transforming the landscape of what interstellar missions might look like. Something that sits at the intersection of artificial intelligence, robotics, and our evolving understanding of what exploration actually requires a human presence to accomplish. We are in the early stages of a revolution in autonomous systems that will, over the coming decades, fundamentally change the relationship between human explorers and the machines they send ahead of them. Robotic precursor missions, highly capable autonomous spacecraft sent to a destination years or decades before any crewed mission, have always been part of serious interstellar planning. The idea is straightforward. Send robots first. Let them survey the destination in detail. Let them establish infrastructure, power systems, communication relays, landing sites, initial resource processing facilities. Then, armed with the detailed knowledge and prepared resources that the robots have assembled, send the human crew into an environment that is at least partially understood and partially equipped to receive them. This approach has been used successfully, though at far smaller scales, throughout the history of solar system exploration. Robotic orbiters and landers surveyed the Moon extensively before Apollo. Robotic missions to Mars have operated continuously since the 1970s, building up a detailed picture of the planet that will inform and support any future human mission. The pattern is consistent. Robots go first, humans follow, when the groundwork has been sufficiently laid. For an interstellar mission, the challenge is that robotic precursors, traveling at the same speeds as any crewed mission, would arrive only slightly ahead of the crew, not enough time to establish meaningful infrastructure before the humans arrive. Unless the precursors travel significantly faster than the crewed vessel, which requires either different propulsion systems or much lighter spacecraft, the reconnaissance advantage is limited. This is one of the reasons Breakthrough Starshot's concept of tiny, fast probes is interesting beyond its immediate scientific objectives. Probes reaching Alpha Centauri at 20% the speed of light, decades before any crewed mission could depart, would provide exactly the kind of advanced reconnaissance that makes a subsequent human mission dramatically more informed and therefore safer. The artificial intelligence dimension adds another layer of possibility. An autonomous robotic system with sufficiently advanced AI, capable of making complex decisions, adapting to unexpected conditions, learning from its environment, and building structures or systems without human supervision, could potentially do more than simply observe a destination world. It could begin preparing it, building shelters, processing local resources, establishing power systems, creating the beginnings of an infrastructure capable of supporting human life by the time the crew arrives, perhaps decades later. This concept, sometimes called in situ resource utilization or ISRU in the space engineering community, is already being actively developed for Mars mission planning. The Mars Oxygen In Situ Resource Utilization Experiment, MOXC, aboard the Perseverance rover demonstrated in 2021 that oxygen can be extracted directly from the carbon dioxide of the Martian atmosphere, a critical step toward both breathing air and rocket propellant production on Mars, without needing to bring those resources from Earth. Scaling ISRU from a shoebox-sized demonstration on Mars to a full planetary preparation system at another star system is an enormous leap, but the principle is established, and principles, in the hands of engineers with time and motivation, have a way of becoming hardware. What all of this points toward is a future interstellar mission that looks quite different from the popular image of a lone heroic spacecraft crossing the void in isolation. A realistic interstellar mission, given the full weight of the challenges we have discussed and the full catalogue of approaches being developed to address them, might look more like a carefully staged, multi-generational program. Early robotic probes, perhaps laser-propelled, perhaps nuclear, perhaps using propulsion technologies not yet invented, sent first to survey, then to prepare, followed by a crewed mission designed not as a desperate leap into the unknown, but as the culmination of decades of preparation, armed with detailed knowledge of the destination, equipped with technologies refined through generations of development, and supported by the accumulated wisdom of every previous mission in the sequence. That is a very different story from the one the movies tell. It is less dramatic in the moment. It is more honest about the timescales involved. It asks more of us, in the sense that it requires sustaining commitment and investment across generations rather than achieving triumph in a single heroic moment. But it is also, I would argue, a more beautiful story in its own way, because it is a story about a civilization making a decision, not an individual, not a government, not a corporation, but a civilization that the stars are worth reaching for, and then doing the patient, unglamorous, extraordinary work of actually reaching for them. We are, right now, at the very beginning of that story, the first page, maybe the first paragraph. The technology we have today is to interstellar travel what the Wright brothers' flyer was to transcontinental aviation, a proof of concept, a demonstration that the physics work, a first trembling step in a direction that will eventually lead somewhere that the pioneers themselves could not fully imagine. Orville and Wilbur Wright made their first powered flight at Kitty Hawk in December 1903. 66 years later, human beings walked on the moon. The pace of progress in aerospace technology across that span was so rapid, so non-linear, so driven by the compounding effects of accumulated knowledge and competitive motivation, that no one standing at Kitty Hawk in 1903 could have predicted 1969. No one. We are standing at our own Kitty Hawk right now. The interstellar equivalent of 1969, whatever that looks like, whatever technology makes it possible, is somewhere ahead of us. Not visible yet from where we stand, but real. As real as the stars themselves, which have been burning patiently in the dark for billions of years, waiting without waiting, indifferent to whether we come or not, but ready to be known by anything curious and persistent enough to make the journey. Let us talk about what it actually means to be the generation that asks these questions, not the generation that answers them. We are almost certainly not that. Not the generation that builds the ships or trains the crews or watches the launch from some future spaceport on a morning that none of us will live to see. But the generation that asks, the generation that looks at the universe with instruments powerful enough to see its true scale, understands what that scale implies about our place within it, and chooses, deliberately, consciously, with full awareness of how hard the road ahead is, to take the question seriously. That choice matters more than it might seem, because the history of human achievement is not, at its deepest level, a history of technology. It is a history of decisions made by people who could not see the outcome, who had no guarantee of success, who faced ridicule or indifference, or the simple grinding resistance of a world that did not yet believe in what they were trying to do. Every major leap forward in our understanding of the universe, from Copernicus placing the sun at the center of the solar system in the 16th century, to Edwin Hubble demonstrating in 1924 that the Andromeda Nebula was a separate galaxy millions of light years away, to the detection of gravitational waves by the LIGO collaboration in 2015, confirming a prediction Einstein made 100 years earlier. Every one of those leaps began with a decision to take a question seriously, to fund it, to staff it, to protect the time and space needed for the slow, uncertain, frequently frustrating work of actually finding out. The interstellar question is at that stage right now. It is being taken seriously by a growing community of scientists, engineers, and thinkers whose work is grounded not in wishful thinking, but in rigorous physical analysis. Organizations like the Tau Zero Foundation, founded by scientist and author Mark Millis, who previously led NASA's Breakthrough Propulsion Physics project, exist specifically to advance interstellar research in a scientifically credible way. The British Interplanetary Society has been publishing serious technical analyses of interstellar mission concepts since the 1930s, including the landmark Project Daedalus study completed in 1978, which produced a detailed engineering design for an unmanned fusion-powered interstellar probe that remains one of the most thorough such analyses ever conducted. The Initiative for Interstellar Studies, based in the United Kingdom, continues that tradition with modern technical rigor and an active international community of researchers. These are not fringe organizations populated by dreamers disconnected from physical reality. They are communities of engineers and physicists and biologists and social scientists who understand precisely how hard the problem is and who believe, on the basis of careful analysis rather than romantic optimism, that it is solvable, not soon, not easily, but solvable. And the distinction between a problem that is merely very hard and one that is genuinely impossible is the most important distinction in the history of technology. What would it actually take, in practical terms, to move the Interstellar project from its current early conceptual stage to something resembling a real program, not a crude mission that is centuries away at minimum, but a genuine, coordinated, well-funded research effort aimed at solving the foundational problems we have been discussing throughout this video. The answer, when researchers address it honestly, involves several converging threads that need to develop in parallel. The first is propulsion. Without a propulsion system capable of achieving at least a few % of the speed of light, everything else is academic. The most promising near-term directions involve nuclear, specifically nuclear pulse propulsion variants that improve on the Orion concept using more refined explosion geometries, and nuclear fusion propulsion that harnesses the same energy source as the stars themselves. Progress on fusion energy for terrestrial power generation, accelerating rapidly right now, driven by both government programs and well-funded private ventures, will produce knowledge and technology directly applicable to spacecraft propulsion. Every advance in plasma confinement, high-temperature superconductors, and compact reactor design that the fusion energy industry generates is an advance that the interstellar propulsion community can draw on. The two fields are not separate. They are the same physics applied to different contexts. The second thread is radiation biology, understanding at a mechanistic level exactly how ionizing radiation damages biological systems and exactly what interventions, whether pharmaceutical, genetic, or behavioral, can protect against that damage, is a research area with enormous terrestrial relevance beyond spaceflight. Cancer treatment, nuclear medicine, and the long-term health management of radiation workers all benefit from the same fundamental research. The investment required to push radiation biology to the point where a multi-decade interstellar voyage becomes biologically survivable is not purely an investment in space exploration. It is an investment in medicine at large. That overlap makes it easier to justify and easier to fund than a narrowly space-focused program would be. The third thread is closed-loop life support. Building systems capable of indefinitely recycling air, water, and nutrients in a closed environment with no external inputs is a challenge that resonates far beyond interstellar travel. A planet under growing environmental pressure, facing resource constraints, and the need to dramatically reduce waste and consumption has every incentive to invest in exactly the closed-loop thinking that an interstellar mission demands. The technologies that would keep a crew alive between the stars, advanced water recycling, atmospheric processing, food production in controlled environments, complete waste remediation, are the same technologies that a sustainable civilization on Earth will eventually need to develop and deploy at scale. The interstellar life support problem and the terrestrial sustainability problem are at their core the same problem expressed at different scales. The fourth thread is artificial intelligence and autonomous systems. A spacecraft crossing interstellar space cannot wait for instructions from Earth. Every critical system must be capable of monitoring itself, diagnosing problems, identifying solutions, and implementing those solutions without human input or with minimal human input from a crew whose own cognitive resources are finite and cannot be devoted entirely to systems management. The development of truly robust, reliable, long-duration autonomous systems is arguably the deepest and most consequential engineering challenge in the Interstellar project, and it is also one of the most active areas of research in the broader technology landscape. The progress being made in artificial intelligence, in machine learning, in autonomous decision-making, in robust systems that can operate reliably in novel and unpredictable environments is directly relevant. Not the narrow AI of today, impressive as it is in specific domains, but the kind of genuinely general, adaptable, reliable artificial intelligence that researchers are working toward. Building AI systems that can manage an interstellar spacecraft across decades is the hardest version of a problem that the technology industry is already deeply invested in solving for far more mundane applications. What is remarkable, when you lay these four threads out side by side, is how much of the necessary work is already happening, not because of interstellar ambition, but because each thread has compelling near-term motivations of its own. Fusion energy research is being driven by the need for clean, abundant power on Earth. Radiation biology research is being driven by cancer medicine. Closed-loop life support research is being driven by sustainability concerns and near-term Mars mission planning. Autonomous systems research is being driven by commercial applications from self-driving vehicles to industrial robotics to financial systems management. The Interstellar project, in this sense, is not waiting for humanity to decide to invest in it. It is being built piece by piece by a civilization investing in its own immediate needs, with the interstellar application emerging as a consequence of that broader progress. This is perhaps the most hopeful observation we have encountered in this entire exploration. The path to the stars is not a detour from human civilization's development. It is the natural extension of it. Every technology, every insight, every hard-won piece of understanding that we develop in the service of living better on this planet brings us, incrementally but inexorably, closer to the capability required to leave it. Now, there is a philosophical thread running through everything we have discussed that I want to pull into the open because it deserves direct examination rather than just the oblique references we have made to it along the way. It is the question of whether interstellar travel, given everything it costs and everything it demands, is the right thing to do. Not whether it is possible, not whether it is technically feasible, but whether it is right. This question has several layers. The first is the layer of resources, the investment required to develop the technologies for a genuine interstellar program, even spread across a century of gradual development, is enormous. Critics of space exploration in general, and of ambitious deep space programs in particular, have long argued that those resources would be better spent addressing immediate human needs on Earth. Poverty, disease, climate change, the catastrophic loss of biodiversity, the billions of people who lack access to clean water, adequate nutrition, and basic health care. Against that backdrop, spending on a program whose practical benefits to ordinary people are indirect and long delayed can seem like a profound misallocation of moral priority. It is a serious argument and it deserves a serious response, not a dismissive one. The response that I find most honest is not that space exploration is more important than addressing human suffering. It is not, in any direct sense. It is that the framing of the choice as a binary, as either or, misrepresents how human civilization actually allocates resources and generates progress. The technologies that have flowed from space exploration, from satellite communications to GPS navigation, to the miniaturization of electronics, to advances in materials science, medical imaging, water purification, and weather forecasting, have created economic and social value that dwarfs the investment in the programs that generated them. The long-term, indirect benefits of fundamental research and technological development are consistently underestimated by analyses that look only at immediate costs and near-term returns. And there is a deeper point, one that Carl Sagan made with characteristic elegance and that has stayed with me since I first encountered it. The Earth is a fragile world. Its history is punctuated by mass extinctions, 5 of them so severe that they eliminated the majority of species alive at the time, and one of them, the end Permian extinction approximately 252 million years ago, came close to ending complex life on this planet entirely. The causes of those extinctions were varied: asteroid impacts, volcanic eruptions, rapid climate shifts, but they shared a common feature. They were indifferent to the complexity, the beauty, or the potential of what they destroyed. The universe does not grade on effort. It does not reward intelligence or creativity or love with protection from its own chaotic processes. Becoming a multi-planetary and eventually an interstellar species is the only long-term insurance policy available against the kind of catastrophic, civilization-ending events that the geological and astronomical record tells us are not merely possible but historically inevitable on long enough timescales. That is not a reason to ignore present suffering. It is a reason to pursue both, to work urgently on the immediate challenges of human welfare while simultaneously building, slowly and carefully, the capability that ensures there is a future in which that welfare can continue to be pursued. The second philosophical layer is more personal and in some ways more difficult. It is the question of what we owe to the people who would actually make an interstellar journey. Not to the civilization that sends them, not to the science that would benefit from their mission, but to the individual human beings and their children and their children's children who would spend their lives crossing the void between stars. For a generation ship, this question becomes almost unbearably acute. The founding crew makes a choice, perhaps the most consequential individual choice any human being has ever made. They volunteer for a mission from which there is no return, to a destination they will not live to see, knowing that their children will inherit a mission those children never chose, knowing that every subsequent generation aboard the vessel will be born into a life defined by someone else's decision made before they existed, that they have no power to unmake. Is that ethical? Does the potential benefit to the species, the preservation of a branch of humanity, the extension of our presence to another star, the scientific knowledge gained, the simple fact of having done what seemed impossible, justify asking people to live and die for a goal they did not set? The philosopher Derek Parfit, whose work on personal identity and future generations remains deeply relevant to these questions, would probably say that the ethics of such a decision resist easy analysis using our ordinary moral frameworks because those frameworks were built for situations where the identities of the people affected by a choice are fixed, and a generation ship creates the people who will be most affected by the decision to launch it. These are genuinely hard questions. I am not going to pretend they have easy answers, because they do not. What I will say is that the history of human exploration is full of people who chose journeys from which they might not return, who brought children into environments of risk and hardship, who made decisions for future generations that those generations could not ratify in advance. The families that crossed oceans in leaky wooden ships to settle unknown continents made choices for their descendants that shaped those descendants' entire lives. Whether they had the right to do so is a question that philosophy has been wrestling with for centuries without reaching consensus. What seems clear is that any serious interstellar program would need to grapple with these ethical dimensions as rigorously as it grapples with the engineering ones, not as an afterthought, not as a public relations exercise, but as a genuine, foundational component of mission design, because a mission that solves every technical problem but fails to build ethical legitimacy is a mission that civilization will not sustain across the generations it requires. And then there is the third philosophical layer, which is perhaps the most expansive and the most difficult to articulate without slipping into language that sounds more like poetry than argument. It is the question of what interstellar travel means for our understanding of what we are. Every major shift in our picture of the cosmos has produced a corresponding shift in our picture of ourselves. When Copernicus removed the Earth from the center of the universe, it was not just a change in orbital mechanics. It was a change in the story humanity told about its own significance. When Darwin demonstrated that human beings are not separate from the rest of life on Earth, but continuous with it, shaped by the same evolutionary processes, sharing ancestry with every other living thing, it was not just biology, it was a redefinition of human identity. When Hubble showed that the Milky Way is one galaxy among billions, each containing hundreds of billions of stars, the scale of the universe expanded not just in our maps, but in our sense of our own smallness and, paradoxically, our own wonder. Interstellar travel, the actual physical act of crossing the space between stars, of becoming a civilization that exists at more than one stellar address, would produce a shift of comparable magnitude, maybe larger, because it would not just be a change in our understanding of the universe, it would be a change in our relationship to it. We would no longer be inhabitants of a single star system, looking outward with instruments and imagination. We would be inhabitants of the galaxy itself, participants in the cosmic story at a level that nothing in our current experience comes close to. What that does to a species, how it changes what we value, how we govern ourselves, how we relate to each other and to the other forms of life we share the universe with, is something we cannot fully predict. But if the history of exploration teaches us anything, it is that the act of genuinely going somewhere transforms the people who go in ways that staying home never could. The astronauts who have flown in space consistently describe the experience as permanently and profoundly life-altering, not just because of what they saw, but because of what seeing it did to the way they think and feel and understand their place in things. Scale that transformation to the interstellar. Apply it to a crew crossing 4 light-years of void, arriving at a new star, looking up at a sky full of unfamiliar constellations with a different sun rising over an alien horizon. The Milky Way still there, but seen from a different vantage point for the first time in human history. Home, our sun, our Earth, our entire history. A faint star in a constellation that has no name yet because no human being has ever stood in the right place to draw it. That moment, whenever it comes, will be one of the defining moments in the story of our species. Perhaps the defining moment, the moment when we stopped being, in any practical sense, a planetary civilization and became something genuinely new, something the universe has not seen before, as far as we know. A form of life that started on one world, looked outward with curiosity and courage, and the peculiar stubbornness that seems to be our most enduring characteristic, and crossed the dark to find out what was on the other side. We are not there yet. We are so far from there that the distance is almost comic when measured against the urgency of our ambition. But ambition unchecked by patience is just impatience, and impatience has never built anything that lasted. What builds things that last is the combination. Ambition and patience working together, generation after generation, each one adding its piece to a structure it did not design and will not complete, trusting that the work itself is the point, and that the completion, whenever it comes, will justify every hour spent on the foundation. That is what we are doing right now. Building the foundation, with telescopes that peer into the atmospheres of worlds 400 light-years away, with fusion reactors taking their first steps toward ignition in laboratories in California and England and South Korea, with radiation biologists studying tardigrade proteins in university labs, with engineers designing closed-loop life support systems for Mars missions that will themselves be practice runs for something much further away, with psychologists documenting the mental landscapes of people who have spent a year in isolated confinement, extracting lessons that will one day inform the design of minds and communities that need to survive for decades in the dark between stars. All of it counts, every piece of it, because the universe, indifferent as it is to our schedules and our impatience, keeps the same rules in every corner of its vast expanse. The physics that govern a hydrogen atom in this room are identical to the physics that govern a hydrogen atom in the interstellar medium 4 light-years from here. The biology that keeps your cells alive and replicating is the same biology that will, someday, need to keep a crew alive across the void. The mathematics that describes the curvature of space-time around our sun describes it the same way around Proxima Centauri. The universe is consistent. It plays by its own rules everywhere, without exception. And that consistency, that reliability, is the deepest reason for hope in this entire story. Because it means that understanding gained here applies there. It means that solutions developed in one context transfer to another. It means that the accumulated knowledge of our entire scientific tradition, built up painstakingly over centuries by curious human beings, asking careful questions and recording honest answers, is directly applicable to the challenge of crossing interstellar space. We are made of the universe. We understand an increasing fraction of how it works, and we are, gradually and with great difficulty, but also with extraordinary beauty, learning to move through it. We have come a long way together in this exploration. From the hull of an imaginary spacecraft drifting beyond the last planets of our solar system, to the biology of radiation resistance in microscopic animals, to the philosophy of what we owe to generations not yet born, to the mathematics of time dilation, bending the very fabric of what we experience as the present moment. We have looked honestly at the obstacles, not to discourage, but because honest looking is the only kind that matters, and we have looked with equal honesty at the reasons for hope, at the research being done right now, today, in laboratories and observatories and design offices around the world, by people who understand the scale of the challenge and have chosen to spend their lives working on it anyway. What I want to do in this final part is not summarize. You have been with this long enough that a summary would feel like an insult to your patience and your curiosity. What I want to do instead is sit with the full weight of what we have been talking about and let it mean something, because information without meaning is just noise. And the story of interstellar survival, the real story, the one that lives beneath the engineering challenges and the biological constraints and the philosophical dilemmas, is not primarily a story about technology. It is a story about what kind of species we are choosing to become. Let us start with something that sounds simple, but is actually among the most profound realizations in the entire history of science. Every atom in your body was forged in the nuclear furnace of a star, not metaphorically, not poetically, literally, physically, chemically. The carbon that forms the backbone of every biological molecule in your cells was produced by nuclear fusion reactions in the cores of stars that lived and died before our sun was born. The oxygen you are breathing right now was scattered across space by stellar winds and supernova explosions spanning billions of years. The iron carrying oxygen through your bloodstream at this very moment was created in the final catastrophic moments of a massive star's life, ejected into the galaxy in an explosion so energetic that it briefly outshone entire galaxies. You are not separate from the cosmos. You are not a visitor to it, observing from the outside. You are a temporary but extraordinarily complex rearrangement of the universe's own material, matter that has been cycling through stars and gas clouds and planetary surfaces for nearly 14 billion years, and that has arrived through an unbroken chain of physical and chemical and biological processes at the extraordinary configuration of a conscious human being reading about the stars it came from. That is not a small thing, that is perhaps the largest thing, and it means that when we talk about humanity reaching for the stars, we are talking about the universe reaching for itself, about matter that was forged in stellar cores returning, in a form capable of curiosity and intention and love, to the environment that created it. The journey outward is, in the deepest sense, a journey inward, a return to origin across distances that our instruments can measure, but our intuitions cannot fully grasp. I think about this often when I consider the scale of what interstellar survival would actually require, because the obstacles are real. We have not glossed over them. The radiation environment of interstellar space is genuinely dangerous. The distances are genuinely staggering. The biological challenges are genuinely unsolved. The psychological demands are genuinely unprecedented. The engineering requirements are genuinely beyond our current capabilities. All of that is true. All of it deserves the honest reckoning we have given it. And yet here we are, a species that started on the plains of Africa with nothing but our wits and our social bonds and our peculiar compulsion to ask why, and we have arrived at a moment where we can point our instruments at a planet 400 light-years away and detect the chemical composition of its atmosphere, where we have sent machines beyond the edge of our solar system that are still talking to us nearly 50 years after launch, where we have split the atom, decoded the genome, detected the ripples in space-time left by colliding black holes a billion light-years away, and begun the first tentative steps toward controlling the same fusion process that powers the stars. We did all of that in the blink of a cosmic eye, in a span of time that, measured against the age of the universe, is so short as to be essentially instantaneous. From the first controlled fire to the James Webb Space Telescope took roughly 400,000 years, less than 0.03% of the time the universe has been in existence. The pace of what we accomplish when we apply focused curiosity and collective effort to a problem is, by any reasonable cosmic standard, extraordinary. That pace is not slowing. If anything, it is accelerating. The last 100 years have produced more fundamental scientific knowledge than the previous 100,000. The last 20 years have produced more detailed knowledge of the universe beyond our solar system than all of human history before them combined. The rate at which we are learning about exoplanets, about radiation biology, about materials science, about fusion physics, about the human genome, about the behavior of matter at extreme scales, is compounding in ways that make linear extrapolation dangerously conservative. The world of 100 years from now, if we manage the challenges of the present with even moderate wisdom, will be as unrecognizable to us as the world of today would be to someone standing at Kitty Hawk in 1903 watching a fragile biplane lift off a beach. What that world will have figured out, what specific technologies, what particular breakthroughs, what creative solutions to the problems we have spent this video cataloging is genuinely impossible to predict in detail, but the direction is clear, the physics is consistent, the biology is learnable, the engineering is in principle doable, and the motivation, the deep, ancient, essentially human need to know what is out there, to go see for ourselves, to extend the boundary of the known, and stand at its new edge, looking outward at the next unknown. That motivation is not going away. It has not diminished in all the millennia since the first human being looked up at the night sky and felt that pull. It has only grown, fed by everything we have learned about how vast and varied and full of possibility the universe actually is. There is a version of our future in which we stay, in which the challenges of interstellar travel are deemed too great, the costs too high, the timescales too long for any civilization to sustain the commitment required, in which humanity remains permanently a single star species, sophisticated, intelligent, perhaps extraordinarily comfortable on a well-managed Earth, but fundamentally local, bounded by the gravitational influence of one average star in one spiral arm of one galaxy among hundreds of billions. That is a possible future. I do not think it is our future, but I hold it seriously enough to be grateful that the alternative is being worked on, because the other version, the version in which we do the work, generation by generation, thread by thread, problem by problem, and eventually build our way to the capability required. That version leads somewhere that I find almost impossible to contemplate without feeling something close to awe. Not the shallow awe of spectacular imagery, though the imagery would certainly be spectacular, but the deep awe of genuine transformation, of a species crossing a threshold that once crossed cannot be uncrossed, of becoming permanently and irreversibly something larger than we were. If you are still watching, please subscribe to the channel and give this video a like. Your support means a lot to me. Now imagine for a moment a night sky seen from a world orbiting Proxima Centauri. The star overhead would be small and dim and red, an ember compared to our sun, but it would be a star nonetheless, casting its ruddy light across whatever surface you were standing on. And there, in the constellation patterns of a completely unfamiliar sky, would be one particular star. Unremarkable to the naked eye, just another point of light in a field of thousands, but you would know which one it was. You would have the coordinates memorized, carried across 4 light-years of void to this moment. You would raise your hand and point at it, and you would say quietly to whoever was standing beside you, "That one, that is where we came from." That moment, that specific, quiet, impossible moment, is what all of this is building toward. Not the technology, not the mission architecture, not the radiation shielding, or the artificial gravity, or the closed-loop life support. All of those are means. That moment is the end. The point at which the universe, through us, gets to know itself from a new vantage point. The point at which the pale blue dot becomes visible, not from its own moon, but from another star. The point at which the story of Earth, our wars and our art and our love and our cruelty and our extraordinary, improbable curiosity, becomes part of the story of more than one world. We are not there yet. We need to be honest about that. The path from here to there winds through challenges that will require the best of what our species is capable of, our ingenuity, our patience, our willingness to invest in futures we will not personally inhabit, our capacity to hold the long view even when the short view demands everything we have. It requires a kind of civilizational maturity that we have not yet fully demonstrated, though we show signs of developing it. But here is what I keep coming back to every time I sit with the full weight of these questions. The universe is approximately 13.8 billion years old. Our species, in something like its current form, is perhaps 300,000 years old. We have been doing recognizable science for perhaps 400 years. We have had the technology to leave our planet for less than a single human lifetime. And in that extraordinarily short window, that cosmic instant, we have already sent machines beyond the edge of our solar system, decoded the chemical atmospheres of planets orbiting distant stars, detected the gravitational whispers of black hole collisions a billion light-years away, and begun the first serious scientific work on every major technical challenge that interstellar travel presents. What might we accomplish in the next 300,000 years? In the next 3 million? In the next 3 billion if we are careful and wise enough to still be here? The universe has been patient. It has been running its processes, building stars, scattering elements, assembling planets, permitting chemistry to complexify into biology in at least one corner of its vast expanse, for nearly 14 billion years without urgency, without deadline, without any apparent investment in the outcome. It will wait as long as it takes. The stars will not move significantly in any time frame relevant to our ambitions. The physics will not change. The invitation, implicit in the existence of other worlds around other suns, will remain open. All that is required of us is that we do not give up, that we keep asking the questions, keep funding the research, keep training the next generation of curious people who will push the work forward another increment. Keep looking up, keep wondering, keep choosing, in the face of difficulty and uncertainty, and the very human temptation to focus only on what is immediately in front of us, to also tend to the longer horizon, the one that stretches out past the edge of our atmosphere, past the orbit of our outermost planets, past the heliopause where Voyager 1 crossed into true interstellar space, across the 4 light-years of cosmic ocean that separate us from the nearest other star, and beyond, because out there, beyond everything we have ever physically touched, the universe continues, vast and ancient, and in places violently hostile, and in places heartbreakingly beautiful, and in all places governed by the same consistent, learnable, ultimately knowable physics that we have been decoding here on Earth for 4 centuries. It is not waiting for us, it does not need us, but we need it, in the way that any conscious being needs to understand the world it finds itself in, needs to know where it came from and what surrounds it, and whether it is alone. We are made of it. We are temporary expressions of it. We are, as far as we know, the only part of it that has looked back and recognized itself. And that recognition, that extraordinary, accidental, 4 billion year in the making act of the universe becoming aware of its own existence through the medium of a curious, fragile, stubborn, magnificent species on a small rocky world, is the reason that surviving interstellar space, as brutal and demanding and humbling as we now know that challenge to be, is worth every ounce of effort we can bring to it. The stars made us. It is only right that we should try to return to them. And on that note, this is where we leave this particular journey, not at a destination, but at a beginning. Because every ending in science, every moment where you feel the satisfying click of understanding something deeply, is really just the opening of a door into a larger room. The questions we have explored here lead to more questions, better questions, questions that only become possible once you have sat with these ones long enough to understand what they are really asking. If this kind of exploration speaks to something in you that pull toward the large questions, the deep time, the cosmic scale, then you already know what to do. Keep asking, keep learning, keep looking up at a sky that is not a ceiling but a door, and remember that the universe does not belong only to the professional scientists and the aerospace engineers and the mission planners. It belongs to anyone curious enough to take it seriously. It belongs to you. If everything we just explored got your brain going, then you are exactly the kind of person who needs to click the video on your screen right now. How far could humans really travel in one lifetime? It is the perfect next question after everything we just covered. Check it out. You will not regret it.